Welcome to APEC Open Mic. It's April 27th, and I'm your moderator, Tim Ventura. I want to give a big thank you to everybody who is joining us on today's call, as well as everybody who is watching us on YouTube. So as a reminder, today's session is for open discussion and ad hoc presentations. We don't have any presentations scheduled in advance. We do have a couple of attendees that have emailed me who want to reach out and basically share what they're working on. And we would invite anybody else who's working on stuff to share that as well, if you're open to it, right? Obviously, don't share anything proprietary. Don't give away your secret sauce if you're not comfortable with that. But if you have material you want to share that's related to alt propulsion, this is the place, and we're just trying to keep it live and real. So I'm really excited to get started. I want to start out with a couple of quick reminders. You can view conference replays, details, and speaker info on our website at altpropulsion.com. These open mic sessions are not listed there, at least not currently. These are on our YouTube channel. Usually takes me about a day or so to upload those. So there's a little bit of a time delay, but I try and put those up as well. And I am trying to do my best to put timestamps in so that you guys can easily kind of skip around, right? So during these ad hoc presentations, please try and save your questions for after the presenter finishes. Again, we're trying to keep things mellow and relaxed. And so if it makes sense to jump in, that's totally cool, but we're trying not to interrupt people, right? That way we can help keep things organized. We are using Zoom for this, so you can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. And you can also type your questions into chat. We're going to try and go through those and basically just do our best to stay on top of the chat. Raising your hand is the absolute best way to be noticed, though. So I will go through and call on people in the order that they raise their hand. We're not going to be firm on hand raising unless things get chaotic. So again, if it feels appropriate, if you're not interrupting, feel free to kind of jump in. So again, we're trying to keep things focused on the core topics of the alt propulsion community. So looks like our ad hoc presenters, the folks who were talking about it, have not arrived yet. So what I want to do is, without any further ado, I want to start out with show and tell. Why not? Okay. So let me see. I'm spotlighted right now. So what I'm going to do is share screen. I'll walk you guys through. This is kind of what I'm working on right now. And there we go. Okay. So again, for anybody who may have missed this, and let me apologize, Zoom is throwing up people who are entering the room as we go. So this was the recent debrief article. This is Drew Erigma and Dr. Charles Buehler, Exodus Technologies down in Florida. And they have made quite a splash on the debrief. I helped write this up and I did some interviews. I got this over to Christopher Plain. I want to give a giant thank you to Mika Hanks and Chris Plain for getting this together and out there. So the interview footage alone has had something like 55,000 views. And, this all comes back to you guys. I mean, the work that you guys are doing and the community that you're help growing and, and support and all of that stuff. Thank you for helping to drive this forward. So this debrief article is out there. What they have accomplished is really amazing. I'm a giant fan of Drew and Charlie's work. I think the thing to keep in mind is this is just the first of several projects that are coming together, right? Mark Sokol is working on, he has a big one with dynamic nuclear polarization. I'm actually working on a documentary with that. We also have Jared, Charlie, and several other folks, Mike Gamble, who are working on the Graviflyer. We have Brian St. Clair and Ross Small and several others who are working with inertial propulsion devices. And then we have folks like Michael Perrone who are working on advanced materials as well. So we have a ton of stuff that's under development. This is just one of many, and it is truly exciting. So that's kind of the first thing, just as a reminder. The next thing I wanted to show you, in case you hadn't seen these, I'm going to have to drop a link in here. If you have a Facebook account, this is not secured. This is my collection of Asilomar photos. This is from the trip that Mark David Chester and Michael Perone went on. We all went on this last month. That's us overlooking Big Sur. Mark was kind of a tour guide there. He showed us all the best spots to go. And so this was at the Dynamic Nuclear Polarization Conference, the ENC 65th conference. I am working on a documentary for this. Hopefully it doesn't suck, but I'm kind of learning as I go. And we shot a ton of footage. My role there was just to try and capture what they were doing. What they were doing was truly brilliant. They talked to dozens of scientists. They made an enormous splash, and they opened a lot of minds too, as kind of a fly on the wall. One of the things that I saw was they had people who were just like wide-eyed, you know. So this is pretty basic like photography, but what I should mention is they didn't allow cameras inside the sessions, and they were fairly picky about the presentation sessions where they were explaining things. So most of this is just going to be general trip footage. I will put a link in there. The reason I mention that is in terms of documentaries, I am going down to spend about a week with Jared Yates. And so I'm going to be working on a documentary about the Graviflyer research. I mean, you guys have seen Jared's lab over Zoom, right? So he has a ton of material. He has built many, many of these things. I can tell you that he is burning the midnight oil. In fact, he tried to explain his wake sleep schedule to me, and it involved a lot of caffeine, and it was basically terrifying. So he is doing a ton on this. My goal is, instead of having to like focus on the 720 footage, right, the 720 HD that Zoom puts out, I'm taking down a 4K camera. And so I'm going to do footage that way. And my goal is to try and get as much as I can, and I'll find a way to get this online. Obviously, I'll be making a documentary, but I'm also thinking about ways, maybe I'll just put the raw footage up for you guys to dig through, you know? So we've got that. While we're down there, we're going to be going to McMenamin's UFO Fest, and I am not going to make any promises, we may be able to touch base with Ryan Graves. I emailed Ryan, but ever since he went before the entire world with Congress, he's been like super busy. He doesn't return my emails anymore. I don't know what the deal is. So anyhow, that's coming up. The other thing that's coming up, this is about a week after this, is I'm going to the Scientific Coalition for UAP Studies. This is in Huntsville, Alabama. And again, taking down the 4K camera, I'm going to try and do spot footage. I have no idea what we will see or what's going to be going on there. But my hope is, in the past, David Grush has gone to the SCU conferences. Chris Mellon has gone to those conferences. For anybody who missed it, Chris Mellon just dropped an announcement. He is claiming that basically there is a crash recovery program that's going on. So there's a lot of this stuff that may come to a head at the SCU conference, and that is right at the end of the month. So I'm going to do my best there. The other thing that I'm thinking of, and this would go to Jared's stuff, I'll just skim through this really quick. Yes, this is a cheap commercial. I am looking at probably starting to do basically 360 cam footage. And there are a bunch of different ways to do this, but my thought was this would be something that would be really useful for the Graviflyer. Basically, what you can do is you can put this device on a stick, and you can put it right next to what you're testing, right? So for Jared, that would be the Graviflyer. For Mark's stuff, that would mean putting it actually maybe in the Faraday cage, putting it next to the DNP. You shoot the video, and you can actually reframe that video later and export it. So this is something that I'm looking at kind of getting into. I mean, we've already got all the other cases covered. We're doing 4K iPhone footage and 4K other footage. So, you know, basically this is just kind of a couple of fisheyes that do 360 footage. So that is what I have. I'm going to stop sharing for now, and I will unspotlight myself, and we'll roll from there. What do you guys have? Who wants to start us out?
Can I say something quickly?
Yeah, go for it.
I just want to say that a quick update here. I did have a meeting with the the Five Eyes defense, which is Canada, United States, United Kingdom, Australia, and New Zealand. I did present all my projects, including the anti-gravity one. So they might be interested. So I'm gonna wait for their reply on that. I also presented to investors in Vegas, and I'm gonna ask for grants in Canada. So I might have some funds to move forward with the my especially the anti-gravity project, and also some energy teleportation thing that I started working on the side. So that's just a quick update here. So yeah, so
Thank you, Phil.
hopefully it's gonna hopefully I'm gonna end up in Vegas at some point this year.
Okay. Well, yeah, and you know what? Vegas, if we ever do a meeting, Vegas would be the place to go, wouldn't it? So,
Yeah, definitely they got like important meeting. It's I think it's the some high tech meeting in every January. Some big event there in January. So and but they got some all year long. But mostly is because it's cheap on taxes over there in Nevada. So
yeah. Well, and they do that on purpose. Yeah. I mean,
yeah.
there are a lot of advantages. Nevada has tried to make itself like the center for conferences, right? And part of that is because they want the tourist dollars coming in. They figure people come in for conferences and they'll go to the casinos and, and nowadays they'll see all the tourist attractions and stuff like that. So, and last time I looked, I mean, I tell you, as someone who loves photography, I'm like, what could I do with a giant pyramid with a beam of light coming out of the top? Hmm. Hmm.
Yeah.
So,
Yeah. So yeah, that's it for me.
okay. Well, let me go to Bob. Bob has his hands raised. And again, it's Alt Y on Windows or Option Y on Mac, I believe. Yeah, Alt Y on Windows, Option Y on Mac to raise your hand in Zoom. And there is also a way to do that. I believe it's the Reactions tab. Yes, maybe. But
Hi, my name is Robert Francis Jr., and I've come to the hypothesis that the Biefield-Brown effect is a result of unpaired nucleon spin alignment. I'll start with the origin of unpaired particle spin alignment for those not familiar with it. Magnetism was discovered ages ago, and it was discovered that unpaired electron spin alignment was resulting in paramagnetism or ferromagnetism. In 1915, the Barnett effect was discovered by Samuel Barnett, and he discovered that by rotating an iron bar at high speed, that the iron bar would magnetize. So one way of inducing unpaired electron spin alignment was through high-speed rotation. Then in 1971, GE aerospace engineer Henry William Wallace was the first scientist to discover that the rotation of materials made of unpaired nucleons, in his case brass, generates a field that is not magnetic in nature and does not interact with magnetic fields. Wallace.
Bob.
Yep.
Bob, sorry to interrupt. If you have a slide or something to put up, you can share screen and you can show everyone your slideshow.
I don't have a slide. I just had it on LibreOffice Writer. I have the paper written out on there.
Do you want to do it? Do you want to do a screen share?
Professional. You got a strict, sounded like a presentation because it came off real smooth. So if you've just got it in text, then please proceed. Sorry about that.
Yeah, well, Bob, if you want, you just do a screen share and put up LibreOffice if you feel comfortable with that. You can kind of scroll through it as you give, overviews.
I'm not too familiar with the Zoom.
Oh, yeah, well, so if you click that green square share screen button, and now it's going to bring up a series of windows. There we go. Yeah, perfect.
Can you guys see it?
Yeah.
Okay.
Oh, you write out your intros like I do that too. When I do those interviews, I write out my intro. So
yeah. So Yeah, so Wallace discovered that polarized unpaired nucleons caused nearby unpolarized unpaired nucleons to polarize as well. And one of the things with brass is 100% of the copper isotopes in brass have an unpaired proton. 4% of zinc isotopes in brass have an unpaired neutron. Then in 1992, Eugene Plekhanov built on the work of Wallace with a rotating YBCO superconductor disk that created a field that lowered the weight of the disk. Yttrium in the YBCO has 100% isotopes have an unpaired proton. 17.5% of the barium isotopes have an unpaired neutron, and copper again, 100% with proton, and then less than 1% of oxygen isotopes have an unpaired neutron. In 2020, Eugene Plekhanov continued to build on his work. This time he used a rotating gold-plated aluminum disc that rotated between 8,000 and 12,000 RPMs and generated attractive and repulsive fields depending on the configuration of the disc. 100% of gold isotopes have an unpaired proton, and aluminum again has an unpaired proton, 100%. I ran across this recently. In 2021, R.H. Eskridge directed a research proposal and paper for NASA named A Study of the Pope-Osborn Angular Momentum Synthesis Theory, POEMS, including a mathematical reformulation and validation experiment. And in that, they rotated a disc of bismuth, and it lost and gained an identical amount of weight depending on being rotated clockwise or counterclockwise. So I would say his team proved that there is a polarity to rotationally induced nucleon spin alignment. And of course, 100% of bismuth atoms have an unpaired proton. Now I'll discuss the Biefield-Brown effect experiments. The Biefield-Brown effect was first discovered by Townsend Brown in 1920. In 1929, he submitted an invention, a magazine article called How I Control Gravitation. In the article, he described a capacitor that he had created with two 44-pound lead spheres as the positive and negative electrode, and a glass rod dielectric separating the spheres. He claimed to have motion in the direction from negative to positive electrode when 120 kilovolt DC was applied over the course of 5 seconds. The capacitor was then stationary for between 30 and 80 seconds, and then finally returned to its original position where it would not move for around 5 minutes as it needed to rest, as he called it. While many believe the Biefield-Brown effect is nothing than ion wind due to the prevalence of lifters in the literature, an extremely high volume of wind would be needed to move 88 pounds of lead. And it should be noted that 22% of lead isotopes have an unpaired neutron. In 1953, Thomas Townsend Brown wrote up a research proposal for the Navy called Project Winter Haven. The proposal was for a Mach 3 interceptor craft that was to be energized to 5 megavolts, 5,000 kilovolts. The proposal for a 5 to 10 year research and development program, beginning with a 2-foot diameter disk energized to 50 kilovolts, a 4-foot diameter disk energized to 150 kilovolts, and a 10-foot diameter disk energized to 500 kilovolts. Brown hypothesized the creation of a device he called a flame jet generator to essentially electrify the exhaust stream and generate the high voltages. And he was also proposing the use of barium titanate on the skin of the craft due to its high dielectric constant. In 1957, Thomas Townsend Brown collaborated with the French company Sud Aviation on Project Montgolfier. In communication with the company, I found this on in a link on archive.org. In communication with the company, Brown stated that dynamic applications of the Biefield-Brown effect had been classified by the government. Dynamic applications could refer to propulsion systems and or the use of pulsed voltages rather than static ones in the capacitor experiments. In 1991, Robert Talley, funded by the Air Force, conducted experiments at 19 kilovolts on capacitors with an acrylic dielectric and a PZT dielectric. Tally measured no movement with the acrylic capacitor until he used pulse voltages, and even then, only at the highest pulse rate of 600 hertz did he get a result with acrylic. Tally measured multiple movements of the PZT dielectric as the current pulsed through the dielectric several times a second, as its dielectric strength was not enough to prevent breakdown. Acrylic, 1% of carbon atoms, less than 1% of carbon atoms have a neutron, less than 1% of oxygen isotopes have an unpaired neutron, but greater than 99% of hydrogen isotopes have an unpaired proton. PZT, it's made of lead, which is again 22% have an unpaired neutron. Zirconium, 11% of the isotopes of zirconium have an unpaired neutron. Then 12% of titanium isotopes have an unpaired neutron. And again, oxygen. In 2008, Taki Musha described an experiment by the Honda R&D Institute with a capacitor with two different voltages applied. One voltage was a static DC at 18 kilovolts, while the other was a pulse DC at 8 kilovolts and at 50 hertz. The pulse capacitor experienced more weight loss despite half the voltage being applied in the experiment, indicating that pulse voltages have higher propulsive capabilities than static ones. Now, a government UFO that ties together unpaired nucleon spin alignment with the Biefield-Brown effect. In 1988, Brad Sorensen, according to Mark McCandlish, or Leonardo Sanderson, according to Gordon Novell, leaked to his friend Mark McCandlish and Gordon Novell the existence of the alien reproduction vehicle. He reportedly saw it at an air show thanks to being an aide for a prominent DoD official. The presentation was for the politicians and bureaucrats with a need to know in an effort to get their support for funding the production of a series of ARVs for the military. There are 3 models of the ARV, all with the same outer appearance, but in 3 different sizes. A general giving the presentation on the craft stated it was capable of light speed or better. It is unclear if this was relegated only to the largest model. According to Novell, he also stated that a state change occurred in the ARV when voltages of 1.2 megavolts were used. No explanation of what happened with the state change was given. A side panel on the ARV was open to the audience to look inside the craft. At the bottom of the craft, there were what looked like 4 layers of parallel plate capacitors. The capacitors did not use thin, flat metal electrodes as would be expected if the Biefield-Brown effect was solely due to, say, energy stored in the capacitor. Instead, the electrodes in the ARV's capacitors were ½ an inch thick and appeared to be copper. My hypothesis is that parallel plate capacitors put stress on the dielectric between the electrodes, causing atoms and molecules to turn into electric dipoles, with the electron clouds being pulled towards the positively charged plate and the nuclei being pulled to the negatively charged plate. This causes the axis of spin of the electric dipoles to be perpendicular to the capacitor plates. It is my hypothesis that the electric field of the capacitor polarizes the spin of the unpaired nucleons in the dielectric, like rotating material with unpaired nucleons at high speed did under Wallace. With Wallace, higher rotation speed increased alignment all in one direction. In capacitors, higher voltage increases alignment, with high enough voltages fully aligning the unpaired nucleons in the capacitor dielectric as well as in the metal capacitor plates. Perhaps full alignment occurs at 1.2 megavolts, but the voltage may depend on the dielectric used and its thickness. The alien reproduction vehicle's nickname was the flux liner. Perhaps it had that name due to pulsed DC voltages being used applied to the capacitor array rather than static ones. Final thoughts. All things being equal, the higher the percentage of atoms making up the capacitors that have unpaired nucleons, the better. The case may be that atoms with higher atomic numbers provide better propulsive force when their spins are aligned. This could be due to either their mass having some sort of effect or the energy of the unpaired nucleon having an effect, as the higher the atomic number, the higher the orbital velocity and energy of that unpaired nucleon. I intend to use PVDF as the dielectric in my experiment. While its dielectric constant is between 8 and 10, 66% of its atoms have an unpaired proton. It also has a high dielectric strength. Kynar 740 is a variant of PVDF, and it has dielectric strength reported at 1600 kilovolts per inch. The metal capacitor plates will be aluminum, whose atoms have an unpaired proton, and they'll be 1/2 inch thick. The theoretical voltage I'm currently aiming for is 630 kilovolts. I will place scales with a weight directly above and below the capacitor to determine if any forces are being emitted out of the top of the bottom of the capacitor, assuming things get positive results. Absolute final thought: in order to accelerate replication of my experiment by others, assuming it has significant positive results, I intend to share all files and designs related to the construction of the experiment, including all the off-the-shelf tools I used, the tools I designed and built, the Marx generator, the parallel plate capacitor, the harness to suspend the capacitor and report the capacitor's weight when the experiment is active, including like STL files, Fusion 360 files and stuff like that. That's it.
Awesome. Awesome. Okay. So let me do this. I'm going to stop your, let me stop your screen share real quick. Bob,
Okay.
that is awesome. And oops, sorry about that. Wrong button.
That's okay.
Ask to start video. There, stop sharing. Okay. Sorry about that. There we go.
There you
Yeah.
go.
So a lot of the stuff, especially in the beginning, that it seems like that relates very closely to what Mark Sokol was working on.
Yeah,
But
unpaired nucleon spin alignment. Yeah.
yeah, so I should ask, does anybody have any thoughts, questions, comments, feedback for Bob?
Oh, heck yeah. Actually, I've got one that I don't know if you're aware of this, but have you read through all Brown's notes? Have you read his notebooks?
No, I haven't read his notebooks, no.
Oh man, take the time. I mean, you've already stumbled across almost all the major points that you need as a backing to make this work, which is really awesome. I didn't hear you mention gravitational isotopes versus inertial isotopes, and that's one of the things that you'll find in notebook number 1 and also covered in number 2 for the methods or mechanisms of separating the two from each other. The difference is when you apply an even gravitational force to a gravitational and an inertial isotope, in a gravity field, they'll both seem to have the same mass, but when you apply an acceleration force to them, they'll have different responses to that acceleration that don't match their mass, effectively making them a claimable violation of Einstein's equivalence principle. Some of them will get heavier under acceleration, as in they'll act as if they weigh more than they actually do, and so they won't accelerate as much, and some of them will act as if they weigh much less, even though gravitationally they still may appear to be the same in a static condition. So it's the difference in relative reference frames, and that could have to do with the displacement of the unbound nuclei or the unbalanced nuclei. So just read his notes. If you haven't, like you said, you haven't, definitely take the time to do it. They're up on Rex Research and available also on the Thomas Townsend Brown family website. So check it out, dude. You're going to find out a lot that's going to help.
Awesome.
All right, sorry, have you decided to use capacitors with in your research, or?
Oh man, I have a long 23 years in this now, playing around with T.T. Brown and Tesla stuff. So yeah, we've tried asymmetrical capacitors and many different varieties of dielectrics, differences in thicknesses. Using leaky dielectrics, for example, is another different approach that we've seen from the Horizon Drive. So there's lots of different ways to approach it. Ultimately, what we're looking for is sort of 3 main things. We're looking for nuclear spin, which can be idealized by using odd nucleon isotopes.
Yeah.
Second, we're looking for asymmetrical acceleration of charged particles that have a sudden velocity change. In this case, like the Horizon Drive, they accelerate through the medium of the kapton or polyamide tape, and by the time they reach the anode, the electrons are traveling at such an insane velocity because the electric field between the cathode and the anode at that point for like a 6 micron or a 12 micron thick tape is so intense. So they reach near relativistic speeds, and they do this over such a short period of distance that they create an information horizon, as in a cutoff point, a bubble, if you will, where anything that's past that point won't get affected by their acceleration force. Things that are within it can actually be accelerated just in the same way that Wallace noticed, where you have this connection between the spin of one and the spin of the other. And just by accelerating the electrons, you put that onto a linear directed. So that would be your second point. And then the third point is we need to recognize the velocity of light and its importance in creating differential field forces. So in a gradient field drive that has an alternating potential on it, the field from the anode and the field from the cathode, if they're changed fast enough, will both have to travel through space and reach each other at some delay at the velocity of light based on their spacing apart. The thing is, you can create signals faster than the amount of time it takes for light to travel between the electrodes. So you can produce an asymmetric force that's not actually in violation with Newton's principle, since they are pretty much founded upon the same ideas as conservation of energy and conservation of momentum and the laws of thermodynamics. All require a closed system and all require all active components of that system to be in the same frame of reference. And in this case, all those rules are broken. So these limiting laws don't really apply to these types of test cases, if all that makes sense.
No, a lot of that was over my head, but I was wondering if asymmetry is necessarily needed, because I mean, I know with the alien reproduction vehicle, I mean, like each layer of the capacitor plates were angled a little bit. I thought that had more to do with the coil and stuff and directing matter around the craft, and that, you know, polarizing the nucleons, you know, that it wouldn't make a difference if it was a symmetrical or asymmetrical capacitor. But I haven't gotten to the point of creating any capacitors yet. I was just putting together my CNC router to start milling components today.
Your question about asymmetry is a really important one. You can do it with the properties of a gradient field. So an asymmetrical plate size will produce a gradient field intensity between those two plates. And so you're going to have a very high concentration of electric field potential right near the smaller electrode, and it's going to spread out pretty softly over the larger electrode. So when you consider the instantaneous change in potential surrounding the two electrodes, if you just suddenly make a small signal with a really fast modulation, it's going to travel out omnidirectionally. Well, here's the thing. If both electrodes are fired at the same time, the big electrode, most of its fields are actually going to miss the small electrode. They're going to just travel out past it and through space because they're physically far apart. But the little electrode is going to mostly have its fields on one side hit the large electrode. So you have an asymmetry in time. You have an asymmetry physically in space because they're different sizes, right? And you have an asymmetry in the intensity of the electric field, aka a gradient field drive. It's a type of drive. Electrostatic gradient field drives, magnetic gradient field drives both exist. And there's a lot of patents on them. I even did a presentation a couple years back about them. But that's probably what you want to look into is gradient field drives or gradient reaction.
Jeremiah,
okay,
please turn on your camera. This goes for everyone. If you want to speak, you have to turn on your camera.
Yeah, that would be helpful. Jeremiah has limited bandwidth. That's why I don't hassle him, but we do try and get the cameras going. And I have a bunch of
Kim, you guys, I just want to throw something out there. I don't know if it's important or not, but I built a thruster set out of Kynar a couple of years ago and got, you know, results. There wasn't anything to write home about, and it's a real annoying plastic to work with.
yeah.
So you know, if you want to get together offline, we can chat about this. I can throw up the final test results if anybody wants to see them.
Yeah, and Drew, do you think you could drop your contact or your email into chat, and Bob could use that? And if it's okay, I have a bunch of hands that are up too. So
sure. Oh, I'm sorry, I forgot about the hand thing. Sorry.
Oh no, that's okay. No, we're being kind of mellow. I'm seeing them pile up, so I want to get through them all. Shrish, go for it, sir. Oh, you're muted. There we go.
Yeah. I'm just going to finish what I started last open mic because I thought it was like a 15-minute thing, so I just did something like really fast.
Okay, if that's okay, do you think that we could come back to that after we do questions? Because I think we've got.
Oh, there's questions. I can come back. I mean,
Yeah. So if it's okay, let me stop your screen share real quick. Okay.
Yeah. Stop.
Okay. Yeah. So Shrish, we'll keep your hand up. We'll come back to you as soon as. Let me go through let me go to Jared next. I've got Jared, James, and Ashley. And I should mention we've got a bunch of new folks who are getting involved with APEC. A lot of this comes from the debrief article. So thank you guys for getting involved. For anybody who's not familiar with it, we are open. It's, everyone is welcome. We're focused on making warp drives, gravity modification, all those things a reality. And really APEC is kind of absorbed, I guess, what you might almost call the remnants of several different intellectual engineering and scientific communities. So, that's kind of where we're at. And
So if I can ask Bob a question here.
yeah,
First off, outstanding presentation. I love the amount of research and work you've put into it. It was absolutely awesome. If you could post that a link to that paper in chat or upload it somewhere, that'd be great as a reference document.
I'll put my website and I'll add it to my website. I'll put the site in the robertfrancisjr.com.
Perfect. So my question, I'm hoping I can get an explain like I'm five, like summary of your thing. So as far as I get it, Mark McCandlish-esque type thing, you're taking, slash Biefield-Brown, you're taking parallel plates, you're putting opposing charges, maybe dielectric in between, you're putting super high voltages up to the 1.2, which is coincidentally double the 511 of, the whole electron pairing thing. Yep. So I'm hoping you can kind of give me the explain like I'm five thing on how does having opposing charges how does your restoring force work, right? Where's the conservation of momentum? How do you get opposing charges like that to produce an asymmetrical force? Why does it go towards one side and not the other?
I don't have the answer for that. All I can say is experimental results have shown that. That's where I pulled it from. Where, from like the Poems one with the rotation, depending on the direction of rotation, that's where I got that from. And I just assumed I saw an analogy to the Biefield-Brown effect being, and this that it could be done with positive and negative charges too. It's just a hypothesis.
Sweet.
awesome. Okay, well, Jared, thank you. Let me go to James McConnell next.
Thank you very much, Tim. I just wanted to briefly introduce myself to everybody here and say thank you for Tim for putting this on and for everybody for being here. This is my first time sitting in on one of these APEC meetings, and it's really a cool experience. I actually have just now started a small YouTube show where I do interviews and actually spoke to Charles Bueller last week. So I'm interested in continuing to get involved in this, and I just want to introduce myself to all of you and say that you're welcome to connect with me anytime. You can email me at jamesmcconnellshow@gmail.com. Thank you very much.
Yeah, well, James, thank you. Yeah, I would say drop your email into chat, or whatever contact you feel comfortable with. One of the advantages of Zoom is this does not go up on the internet, right? Like when we do StreamYard, that does go up. So I also feel nervous, but yeah, thank you, man. And
thank you all.
Yeah. Okay. Let me go to Ashley next. Ashley, thank you for being patient, ma'am.
That's all good. Hi, I'm Ashley. I'm brand new into this topic, so I'm probably just going to be asking some very base level questions. So what exactly is like the significance of using pulse versus static voltages to achieve these results that you're hoping to achieve, Bob?
Well, I use the one with there's two Biefield-Brown effect experiments I came across that indicated pulse voltages worked better. The one was the Takamusho one I mentioned in my presentation, where they got more of a propulsive effect with the 8 kilovolts pulsed than they did with the 18 kilovolts static. There's another one, I didn't include it because it was about lifters. It was like a lifter, but he I don't remember the name of it. I got it somewhere. He tried using static DC, and then he found when he was applying pulsed DC that he got just as much weight loss, but it used less electricity, less wattage.
Oh, okay, so it's just kind of more of a like efficiency versus like power output almost, or?
Yeah, I guess. Or I mean, like I also said, the ARV was called the flux liner. I mean, who knows why it was called the flux liner, but fluctuating voltages that just resonated with me.
Okay. Thank you.
And Ashley, I can speak briefly to that. I did a lot of work with lifters back in the day, and one of the things that we found was those were powered by Cockcroft-Walton voltage multipliers. Those create a pulsed sawtooth DC waveform, and so it literally looks like the blades of like a saw, right? And that was kind of what everybody was starting out with, and so that was what we considered normal. And when people started to build their own power supplies, it got a little bit more complex. They went to static DC, and we found that it didn't perform as well. So at least in that particular device, and that was a mixture, there was what I believe is some Biefield-Brown as well as a lot of ion wind involved with those. So it was very complicated and messy and confusing. But the impression that everyone I know had was that the pulse DC was the best, and for all of us, that was kind of what we started with, so we considered that normal.
Yeah. Okay. Awesome. Thank you very much, guys.
Okay. Let me see. So, Shrish, did you want to do your presentation?
Sure.
And okay, awesome. And thank you, everybody, for being patient.
Yeah, it's just one slide actually speaking, because I'm just.
Oh, yeah, go for it. Go for it.
Okay, let me get that back. Okay. So just briefly, I was just mentioning about an equivalence principle violation or non-equilibrium the last time. So it's based on, I mentioned this in a few of our discussions. So I just wanted to bring this up because actually a few of the scientists have looked at my talk the last time, and they were concerned that I've not given enough attribution. So here it is. Okay, so I didn't know anyone is going to look at it, but people are. So basically, symmetry breaking, that's the foundation of what I'm doing. Essentially, Pinheiro has come up with this paper, I think a decade ago, called On Newton's Third Law and its Symmetry Breaking Effects. So it's actually a very interesting one, really, because what it is in brief, it's a self-engine. There's a thermal differential between ends. There's a non-equilibrium entropy gradient in velocity space, and this canonical momentum of the particles is bounced between the ends. And what he says is there's an inertial vacuum background change in momentum, which produces this symmetry breaking. So in really brief terms, it says that in systems out of equilibrium, Newton's third law is not verified, and a third system must be added to account for conservation of momentum, which is the inertial background or vacuum, etc., really speaking. So I just showed this thing here. So you see the first one is basically what we have for normal conservation of momentum, Newton's third law. Delta rho 1 is equal to delta rho 2. Okay, so supposing we have the conditions in the second bullet, then we have this third term called this delta rho v, which is the vacuum effect. And what he says is, with this, we can provide this delta rho v, since it's coming from the context of the vacuum, is propulsion, essentially speaking. So the system itself is moving under this delta rho v. So what is interesting about this is energy and momentum, which is coming out of the context of the system. So that is basically, there's no ZPF here, there's none of that stuff. This is actually due to conservation of momentum, really speaking, but it's coming in free. So if you look at it over time, as delta rho 1 and delta rho 2 are constantly repeating, delta rho v will continuously increase from the vacuum. So that's basically what I mean by, one of the things that I mentioned in my last presentation was this, that, the energy needs are much lower than conventional propulsion if you can use the vacuum in the right way. And that is not using ZPF or anything like that, but using this delta rho v or Pinheiro's model, really speaking. That's basically what it is. If anyone wants to know more, you can look at the paper. I've given a link to that. So, but I think it's quite fascinating in terms of its potential for propellantless. And of course, I've enhanced it to be possibly an alkublary kind of model. But the big thing that I like about it is propellantless, and that energy is coming in from the outside, really speaking, without violating any laws, really speaking. So that's the end of my talk.
Awesome. Shrish, thank you. Thank you.
Yeah.
Yeah, so let me stop the share on that.
Yeah.
And yeah, does anybody have questions on Shrish's presentation, on his update?
I assumed as much. Anything with thermodynamics is a bit weak out here.
Oh yeah, no, it's okay. Well, you know, we're relaxed today too. So
No,
Okay. I had to do
Oh.
that because someone wanted it. So
yeah,
go ahead.
actually, Daniel, go for it.
so you're sorry. So you're kind of sort of trying to find like a warp drive equivalence and through thermodynamics instead of general relativity, right? Because there's an equivalence there. Like
Actually speaking, what I just showed was a propellantless method, and then I've enhanced that to show, if you look at my last week's talk, I'd mentioned about a positive and negative inertia model, which can be considered as an equivalent to Alcubierre's warp drive when you look at it from an inertial point of view. So yeah. So the mechanism for that is, the underlying mechanism for that is this thermodynamic method that Pinero has shown, really speaking.
see, because to me that's kind of interesting because in the how the many worlds principle, not to get into that, unifies with general relativity is through thermodynamics. And
Right.
so where you get the, the area proportional to entropy is equivalent to the G mu nu times T mu nu. So I've been really curious. That's something I've been really curious about, is trying to find, how we could find an equivalent of Alcubierre on this. We should probably email at some point.
Yeah, sure. Yeah, I mean, definitely, I believe, as Einstein said, thermodynamics is our foundation, really speaking. Everything builds up over that. And there's a lot of this connection with thermodynamics and Einstein's equation of state, and this theory that I showed the last time is based off that, so it's definitely connected. I mean, I think if we bring it in together, that's when we should see the effects, really speaking. Because what I'm trying to say is, from last week, is Alcubierre's warp drive is actually, at its most basic, as I have defined it, it's a non-equilibrium in the equivalence principle, and that is why we have the effect of the warp drive, really speaking. Okay. I mean, how do we get there? This is without violating any energy conditions, etc. Because those energy conditions, the negative energy, etc., is coming in from the vacuum, really speaking. Okay, so there's been various papers about this. Is something that we have to produce the energy to break the fabric of space-time, or the energy is there in the fabric of space-time, and that has to be harnessed in some way. And one way is through this non-equilibrium that I'm proposing, building up of Pinero. And I think that's the more scalable long-term way, really speaking, because we can't keep on putting in all the energy we need inside our little propulsion system, is the whole angle that I've been going at. And this model that I showed, it shows that, there is a way to tap into that external infinite energy, really speaking, without violating anything or trying to poke into the ZPF and other techniques that have been talked about before. So that's my bandstand view.
Awesome. Okay.
I had a question on that.
Oh yeah, go for
it. So, I'm coming really fresh to all this, but so under normal circumstances, Newton's third law holds that every action has an equal and opposite reaction. That's actually like a demonstration of the symmetry. So like trying to understand what I'm seeing, if I understand your understanding, which is what you're proposing is that under systems that are out of equilibrium, that same law may actually produce asymmetrical results in the external. Is that more or less, or
almost? So basically, conservation. So what he's talking about, say, let me just rephrase that. I'm building up an implementation of what he's proposed, really speaking. And what he's saying is Newton's third law, when a system is out of equilibrium, okay, that's the most important part. Under equilibrium, it is exactly as you mentioned, right? I mean, equal and opposite reactions. But when it's out of equilibrium, you have to include a third system, which is the topic of his paper. He talks about various other things in that paper of his, with Abraham and lots of other things with electromagnetism, etc., where he talks about this third aspect, right? You got to include the third aspect, which is the vacuum. Okay, so when you include the third aspect, then Newton's third law is verified. Okay, but you got to include the third one. So basically, it becomes a system plus vacuum model, really speaking. But when you include the vacuum, you have momentum coming in from the vacuum from the outside. So you get momentum of the system, and since that energy to produce that is coming from this vacuum, it is free energy. So it's the same thing as happens in an equilibrium system, that delta rho 1, delta rho 2, that is happening within. But suppose you have this condition, you get it from outside, everything is the same, but now suddenly you got momentum from a free source. I mean, kind of free.
so you're sort of breaking the rules that would normally operate in order to get the system to coax free energy from the vacuum.
Yes.
Okay, that's cool. Thanks for explaining.
Yeah.
Awesome.
Yeah.
Okay, so who wants to go next? Does anybody else have their hand raised?
I guess I'll just have a general question for everybody. I'm sure most of you guys have seen, and if you have seen it, if you had the chance to play with that new Warp Factory toolkit that the Applied Physics Lab and Bobrick's team have put out for it's like a code for MATLAB for programming in different Einstein tensors and then analyzing what the energy requirements are going to be for that. So to make it a little bit easier to do warp drive research. So I've played with it a little bit, not too much. I'm not very good with MATLAB. So is that something you guys have had a chance to look at yet?
No, but I might be interested to play around with it.
Okay. We'll find links and put them in chat for you. I guess here.
Daniel, if you've gotten that to work, I'd love to see some like screen time on it because I still haven't gotten it to work. I installed it, but I haven't been able to get past the first command. It keeps telling me that I have undeclared variables, and I haven't had. It's a factor of time. I just haven't played with it enough.
Yeah, I've never used MATLAB before until I learned about this, so I need to. I'm not the one to ask about that yet.
There is a warp drive simulator. I think I posted on the chat.
Yeah, it's the same
I
thing
didn't
he's
try
talking
it,
of.
but
Well,
sorry?
I think he's talking of the same thing.
It's called the Warp Factory.
Yeah. Anybody tried it out?
This in the chat. Like I said, I downloaded. I don't know enough about the code to actually use it, but I was able to download one of their pre-programmed simulations for the momentum.
I mean, would you want to do like a screen share on it? Do you think would that be worth doing? Or
yeah, sure.
Yeah, give us a walkthrough on it.
Screen share. So pull up this. for right now. So this is the one. So this gives you a good it's a simulation of the momentum flow for the stress energy tensor for this is for the Alcubierre metric specifically. But you can program in any let's see, I gotta find MATLAB. I just get out of this. I'm not very good with the computer. I'm sorry. I should have had this up first. Here, I'll stop the share for a second. Oh, there we go. Now I can minimize that. Wow, stuff to minimize. Okay, MATLAB. Of course, my computer is not going to want to cooperate with me at the moment. Close out some things, see if that makes it go faster. Okay, does anyone here familiar with MATLAB?
Hi, I'm a little bit familiar with MATLAB. I'm Eric, by the way. It's my first time here. I work with Mark Sokol at Falcon Space.
Yeah, I played with it like 10, 15 years ago, but it's been a little while. I mean, I opened it the other day randomly, but I haven't used it much in the past 5 years, I'd say.
Yeah, and what we might be able to come back to that too. Michael Boyd has his hand raised. Michael, did you have just a comment or question, or did you want to share something? I mean, did you have a presentation?
You can let him go while this is loading. This is my computer's slow.
Okay.
Yeah, I just gonna give a little update.
Okay, yeah, go for it. Go for it. Give us an update, and we'll come back to Daniel's stuff. And then Daniel recorded a presentation that we're doing in May, just so you guys know. So
cool. So what I was going to update you guys on is I as you know, I've been working on this paper resolving extra dimensions for gravity. It's under submission to the IEEE Sensors Journal, and in the chat, I'm just put in my email address and a link to the preprint of it. And so what I was going to do, if that's okay with you, is show you what it looks like. Let's see here. Wait a second. I got to do it again. There it is. Here. There it is. Okay, can you guys see that?
yeah. And
Good.
I have this in split screen. This is recording, just so you guys know, I'm recording in split screen so that you can see a larger version of the person speaking also. So if this drives you guys nuts when you come back later, let me know.
Okay, so basically this is Tech RXIV, which is a preprint service for IEEE. That's what I'm a member of. And and you can download the paper. And basically what the paper is about is the weakness of the force of gravity compared to the electromagnetic force, and the other fundamental forces have been referred to as the hierarchy problem. If gravity propagates in several additional spatial dimensions that are large compared to the Planck scale, the hypothesis is that gravity is stronger close up, e.g. below a certain interaction distance, the force of gravity is magnified. In the hard disk drive assembly, the magnetoresistor, MR read sensor in the head assembly operates within 100 nanometers of the spinning disk surface. 14 variable sized nanobumps and nanopits were fabricated on a magnetic disk flattened surface designed to be less than the Planck mass of 21.77 micrograms. These nanofeatures were measured over the spinning disk with both piezoelectric and MR sensors. The data was validated using both atomic force microscope and magnetic force microscope measurements. Results are reviewed and theoretical implications are discussed. The results suggest that the force of gravity is magnified and there are two forms of gravitation. Implications to modified space-time are discussed. And then here as you can see, there's this little disclaimer. They're saying it's not peer-reviewed yet, although that's where it is. And so this is, you can see the article. You can download the article if you want a copy of the PDF. And let me put this down here. And the thing that's kind of relevant to what you were just talking about is the vacuum energy is basically what I'm suggesting is what could be referred to as quantum gravity. And so what the paper has is a lot of data to show the results, but also to discuss the theory, and it relies mainly on this paper that Hal Puthoff put out. It's using his space-time metric engineering principles, and essentially this slide shows what I'm suggesting the results are that we found are that. So basically, what you're seeing on the left here is the nanopits under the disk, the spinning disk, and the little sensor is right there where the arrow points, and what's being formed is the space between causes what's called expands space-time in a little region, and it produced a push force that I could measure with my piezoelectric sensor. And then the opposite effect is observed with the nanobump. As the nanobump goes under the sensor, it actually pulls it down really strong. So, and the reason I show the expanded reason, the expanded spacetime, it's like a bubble, it's like a balloon. It's only strong at the membrane of the balloon, while the nanobump, the denser spacetime region, it pulls like regular gravity, but it's multiplied. So instead of distance squared over time squared, it's distance to the fourth power. It's kind of the fourth power. So it's multiplied. And so basically that's what the paper is about. And I encourage you guys to look at it. And if you want to make any comments, you can do it right there on that page where the link is. And that's basically it. Thank you.
Awesome, Michael. Thank you. So let me see who else wants to go. Daniel, you were loading a paper, or you were loading MATLAB, the warp drive simulator.
Oh, well, that's I need a faster computer. Okay. Well, here I have something up that I guess I can. So I got MATLAB up, but it's kind of giving me issues. Again, I'm not versed in how to use this at all, but I also have both of their papers pulled up around this. So here, let me let's see, go to screen share. And we will start with this, I guess.
Oh, and Jacob was asking in chat how he raises his hand. It's Alt-Y on Windows or Option-Y on Mac. And I think he has a presentation for us. So, okay, so but let's come back to that.
So obviously there's some way to manipulate the code here for where you can use it to simulate metrics for Einstein's equations. And they're using this for can you see? So warp factor, it's a numerical toolkit for the optimization of warp drive geodesics. I'm not gonna go through and bore you with just reading the paper. Let's see. It's not the right one I'm looking for.
So the way they broke this down, from what it looks like, the way they broke this down, basically you just kind of plug the numbers in, right? You kind of pick your model and plug the numbers in, and it calculates for you.
I believe that's the way it goes. Yeah. So here's their other paper. So go scroll down to the conclusion.
And I should also ask, Daniel, were you able to drop a link in chat to this for folks?
Yeah, I already did. So for people can download it.
Yeah.
Yeah,
thank you.
so they have a whole download instruction.
Yeah, and again, it's
there's a get file you have to download for it, and then you have to port it into MATLAB from there.
The warp factory toolkit for MATLAB. For
Yep.
anybody who ends up watching on YouTube later, if you can't read that, it's warp factory toolkit for MATLAB. And I think you said you found that on GitHub, right?
Yes.
Okay.
It's yeah, they're going through and they go through lenses, they go through a few metrics in this paper. Oh, let's see, references. No, I went too far. It's the appendix. I want the appendix B, appendix A. All right, so yeah, down here at the using Warp Factory, the Applied Physics Laboratory team has been exploring more warp space times in a separate paper currently in preparation. A new constant velocity warp drive solution has been found without energy violation, or without the violation of energy conditions. The discovery of this result was made possible by using this toolkit, and so anybody can use this toolkit. They just want you to put it in the references of any papers that you're using this for. So I would encourage you guys to play with this, because I'm sure that you can leverage it much better than I can. And we'll stop sharing from there.
I believe, like, from what I've read, that MATLAB has a limitation. There's like a trial, and after a certain number of days, you have to give it up if you're using the downloaded version. If you don't have like use granted through your university or something like that. But there is an online version that's the one that I'm trying to use that allows you a certain number of hours per week. I think it's like 20 hours per week or something like that. So there's some, it's not exactly freeware, but there's loopholes for those that are not in a university. I haven't even looked into what the full price of the software is.
I mean, really honestly, I think Tim would be a really good person to interview the guys from Applied Physics there about the warp factory.
You can
okay.
generate efficient C++ code with MATLAB as well.
And let me see, Gary Drypen. Thank you, Gary. Gary Drypen. And so I'm going to drop this into chat. I believe that is the. And that's a link to Business Wire. Okay. And we have a fair number of hands that are up. Let me go. If it's okay, let me see. Phil, sorry, go for it, sir.
Thanks, Tim. I just want to say quickly that storing my wrong way is pretty smart. I mean, at some point today, I posted a problem with general relativity, the problem of energy momentum localization, and apparently he already fixed it and posted the, an article peer-reviewed on IOP science. So I'm just responding to to Michael, what Michael was saying earlier. So yeah, he's a pretty smart person, and he's helping me a lot with my own
Okay.
my own manuscript that is being rewritten right now.
Phil, thank you. Let me go to Jared really quick, and then I want to go to Jacob Henry, because I think Jacob Henry had a presentation for us. So
Yeah, I got there we go. I got like a little 3-minute thing to show with the gravel flyer.
oh, okay.
So,
yeah, go for it.
So for anybody who isn't familiar with the gravel flyer, inventor Alexei Chekhov made this thing lift. It's got an ultrasound buzzer on the top. It's got 2 counter-rotating 8-inch discs. There's magnets on the discs. The discs are charged to very high voltage, plus 10 kV, minus 10 kV. You have a Tesla coil attached to the center disc that's operating at about a megahertz, give or take a couple hundred kilohertz. And it's charged to about 2 to 4 kV AC. Anyways, the really short, interesting thing, I was sharing this with some of the other guys in the signal chat. So when you have the distances of the spinning discs spaced just right, we can get like singing, like these resonant singing notes. And I've been trying to like find the theory behind that, because I don't know, it might be in some way related to the mechanism of light. Anyways, what I discovered yesterday was that first off, I went more towards the inventor's very first iterations when he had magnets on both spinning discs. Now he just has magnets on the bottom spinning disc, but I decided to put magnets on the top spinning disc too. When I bring a magnet close to those, simulating the magnetic field of the eddy current in the center disc and the spinning magnets on the bottom, I can get the thing to sing. I'm going to try to see if I can make that happen and get it so it can get picked up on the mic here.
Do you need to clear your throat first? La 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 la.
About as close as I can get it. One more try.
Do, re, mi, fa, sol.
I think Zoom is actually going to block that noise.
Really?
I don't hear anything.
You're not hearing it? It's pretty loud in here.
It's going to filter it out. So what I found is there's a little trick. You got to get your mic close to this noisy source, but a nice clean waveform, you have to produce some other background noise so that it can't filter out the noise that you're trying to actually send over. So you might want to put on some white noise behind it or do something like that to trick Zoom so it stops auto filtering. That's the only way I've ever found to get it through. It's terrible.
All right. I'll give it one more shot here, guys. And if it doesn't work, I apologize for wasting all this time, but I just turned on some background noise of an air filter.
Oh, and I think Bill has a presentation for later. So after I'm mixed. So after, let me see, after Jared finishes, then after Jacob, then we'll go to Bill.
Jared, just really quick. There is an option on Zoom to not remove the background noise. You can turn on original sound. It's in the audio settings.
Yeah, that is a good point. Just remember to change it back after you're done. Otherwise, you'll drive people nuts in meetings all week.
Maybe it was just my device, but even when I turned on original sound and shut off background noise suppression, I still have the same issue where I had to have some kind of sound for it to stop filtering, because it still has some kind of minimal filter it seems to apply regardless of your selection. Maybe it was just me, though.
I have had that experience where I've tried to record myself ohming or doing certain tones, and no background suppression or anything. It just doesn't record. So, maybe technology's got something in for harmonic resonant tones or something.
So I turned off the audio suppression. Is it coming through now?
Nope.
Unfortunately not. Yeah, you might want to put your mic right next to it.
Does it sound like this?
Where the mic is gently, and just when you have the noise in the same exact spot, that might help.
I tell you what, I will post a video to my YouTube channel, Mighty Brain. If anybody wants to see it there, I'll find a way to make sure it comes through on the recording there.
Oh, are you on a Mac
Thanks,
or a
guys.
Windows?
Sorry.
Are you on a Mac or a Windows machine, real quick?
Windows.
Okay, you're on Windows. Well, you can use an audio bypass, which actually allows you to have all of your audio input from your microphone go to a virtual audio device, basically a sound card, that then acts as the microphone according to the software. So it'll see it as a mic, and you can pump it in through that mechanism, and you actually will get your full frequency spread because it won't be operating through the same filters. So that's also an option, and that's done through having that live sound on with no filtering. So, all right, that's it.
Awesome. I'm thinking, as the last thing on this, I'm thinking that now that I have identified, though, that I can cause extra flutter in the outside edges of the disc, I might be able to add in some additional stationary magnets on top of that top disc so that I can make it automatically adjust the height of that to increase the flutter, which is the dynamic spacing between the spinning highly charged disc and the rotating eddy current in the center disc. Anyways.
Are you talking about
Thanks, guys.
motorizing the thing so that you can actually change the height of the discs live or something like that?
Well, that's been on the to-do list for a long time, is to have dynamic adjustable height spinning discs. But there's a whole bunch of problems with that because you're dealing with such high fields. You got to have a lot of shielding. So if I can put in other just stationary magnets that I can, turn a knob and adjust the height on those so that there's no motors involved, it should protect from some of that interference that I'm struggling with.
Yeah, a stepper will not care if it was an isolated battery pack mounted right on the top, and you fed it with fiber optic signal. So, all right, who's next?
Yeah, well, if it's okay, Jacob Henry, sir, thank you for your patience.
Can you hear me?
Yeah, and again, thank you for your patience. You got a present? Do you want to do screen share?
Yes, and I am.
Okay, and I'll put Hal CC's hand down for just a bit.
Sure. Okay. The first thing I want to put out is the capacitance model.
Perfect. Yeah, it looks great, man.
Are familiar with, the two values that people try and change on the capacitance model are the K value, right? The dielectric, and the area, right? And what I'll be talking about is specifically changing the A. Back in 2006, I saw an article on Slashdot, as one does, about a scientist, Dr. Chunli Goel. By the way, I'm terrified, so if my voice breaks and everything like that, please forgive me. Was able to use a femtosecond laser to structure metal in order to change its optical properties. And he was able to achieve not just a red or gold specific wavelengths, but he was able to get a very, very perfect black. And my ears perked up at that. And I gave him a call and asked him if that was due to scorching or if it was due to structure. And he was emphatic that it was due to structure. So the structure itself was able to get a black. And I'm going to now show his video presenting that. Let's see. Here we go. All right, can we see that?
My name is Chunli Guo. I'm a professor with the Institute of Optics at University of Rochester. So my lab, we are using femtosecond lasers as a tool and study laser metal interactions. So I have a couple of research directions pursued in my laboratory. One is very fundamental, actually. We use very high intense laser pulses to study atoms molecules and study the response of atoms molecule in very strong fields, and we're looking at the electron ionization, molecule dissociation, those fundamental processes. And on the other side, we also have more applied research in that direction. So our research really focuses on use high intense femtosecond laser pulses to process the material surface, try to functionalize the surface. And I'm going to give you a few examples. The first one is we developed a technique. We use a laser pulse process a metal surface. Eventually, we produce extensive amount of micro nano surface structures. Those structures are tiny, and even you run your finger across the surface, it still feels smooth. But underneath high power microscope, you see them extensive amount of micro nano structures. So these structures are very interesting. They essentially change the property of the material. And the first thing we did a number of years ago was we dramatically changed the optical properties. So we turn a shiny piece of metal pitch black, which means it's totally become absorptive. Okay? And so light shine upon the metal will not be able to reflect back, so it appears to be black. And so really pitch black. And then after that, we move on technology one step further. We also create something so-called color metal. So the first one, we called it black metal. And the second step, we made this color metal. The difference is for black metal, the surface eventually will indistinguishably absorb all color lights. But in color metal, it was selectively absorb certain lights, color light, but reflect some other colors. So those colors reflect into your eyes, give you the appearance blue, goldenish, or reddish, different colors. So we dramatically just changed the optical property, absorption properties. We know this light is actually, for most people, is
okay. Well, that's the end of the useful part of that. It wasn't just Dr. Guo who sort of looked at this. The next few videos, actually, I might put in the Dr. Kotek's video in between. But of particular note, Dr. Rick Pera from the Air Force Office of Scientific Research also talks about Dr. Guo as a person of interest in 2011, and I've got parts of his speech which I thought were interesting. I'd like to show that now. Just got to make sure I get the right order here.
We're interested in exploring, like I said before, the full. So let me bring this plot, somewhat busy, so I'm going to spend a few minutes on this one. So what I'm plotting here on the left is it's a timeline, and I'm plotting for tabletop systems the achieved focus intensities of these systems. So we start all the way to the invention of the laser in 1960, and then we go all the way to today. And sort of the record is, may not mean anything to you, but it's 2 × 10⁻²2 watts per square centimeter, which is a lot of intensity. Now, if you are all the way down here, so this is where all of your nonlinear optics sits. So this is where you have systems where you have bound electrons and you're exploiting the nonlinearity of your system. If you start increasing your intensity, now you start getting to the damage thresholds of materials. And then you open up the whole concept of doing laser ablation of solids. And then after that, you can think of doing laser machining, laser patterning. And I'm not going to say too much about that. I'll say something, but not too much.
Which is
but
interesting.
It's very interesting because these things machine and pattern in completely different ways than other lasers do. Now, if I continue to increase my intensity, now I actually start freeing up electrons in my system. So my electrons are starting to ionize. And now I start creeping into sort of plasma physics. And in fact, what happens is if I start propagating these things in air, we actually very quickly generate plasmas, and we get things like filamentation. And I'll say more about that in a second. If I keep on turning up this, now we're all the way in plasma, and we get all sorts of really interesting interactions. Now, the way to think about what's going on is ordinary matter, when irradiated with these sort of electric fields, will almost immediately ionize. And then so you have these electrons, they come out, and they actually are left to sort of quiver, and the laser's still on. So they actually left to quiver and actually gain energy from the laser field. So as you go up in this intensity, oftentimes what you're seeing is sort of the effects of sort of these electrons quivering, and then that leads to sort of the subsequent interaction physics. So if you go up, you start being able to do things like generate coherent X-rays or EUV. You can actually generate hard X-rays. You can even generate protons. Now, if I keep on going up, so I'm still sort of down here in the sort of the plasma, we have these electrons that are quivering around. So they start quivering real fast. In fact, they quiver so fast they become relativistic. So this is an area where you're now seeing relativistic effects of the electrons. And this then opens up an entire new set of really exotic interactions. I mean, these have been known for quite a long time. So you have things such as laser wake field acceleration, where you can actually accelerate these electrons to sort of GeV scales in the scale length of about a centimeter. So that's roughly, if you were to do this in conventional accelerators, you need sort of kilometer scales to do the same thing. Now you can do this in a centimeter on a tabletop. You could do this up here if you had one of these things. So very interesting. Then if you keep on going up, now you have these ions, which normally are so massive that they don't really move all that much. We don't really pay too much attention to them. But now they start quivering. And then at some point they start quivering relativistically. So now we're really at the footstep of just a, I'm not even sure what's going to happen when we start looking at these things, to be honest with you. And there's a couple of schemes out there to really push that intensity all the way up. And then you see all the way up here at 10 to the 30th, things like no linear QED. I won't say anything about that, but really interesting physics.
All right, we won't say anything about that. All right. Now, I've got a little bit of a clearer explanation of what he just said from a Dr. Wolfgang Kautek of the University of Vienna. And it's about 4 minutes, but if we think that's valuable, I can play that.
I would vote to play that.
Okay, great.
There's another parameter which is very important, is the wavelengths of light. Very simple, in a linear world, if you have long wavelengths, the penetration depth is long, Lambert-Beer law, you remember?
We don't remember.
And if you have a medium wavelengths, then you have a very narrow absorptivity and a very shallow absorptivity in the UV. So the results of interaction are very different. There you have more melting, vaporization. Here you have shocks. And here you actually breaking bonds if you have polymers or organic material or tissues and so on. So you can play with this. But you can also play, of course, with the length of the pulses, and that will be the topic of the rest of the talk. First, we want to go into the nano world. So you see, we are in the world of viruses, bacteria, viruses, and nucleic acids, and so on. So that's the nanoscale. And if you go into the femto world, then you see we come to the femto with this number of zeros behind the comma, just at the edge between the fastest chips and electronic motion in metal. Okay, well, to give you an impression, you know, in 1 second, light circumvents 7.5 times the globe, and with 100 femtoseconds, yeah, 10 to the minus 13 seconds, light just travels 70 micrometers, and that's half the diameter of a human hair. Okay, but that's the distance. And in 5 seconds, which for instance, near infrared light is the shortest pulse you can get, you only have 2 cycles of the electromagnetic wave. Shorter you cannot go, because then you have no wave anymore. Okay, so these are some features which may be interesting. Now, interaction. And you will see, I will come back always
this really helps explain it right
at the terms thermal and non-thermal. Well, this is just a Mickey Mouse picture to show you if you have long pulses, then you have a long-lasting interaction of the laser light, and therefore heat, which is dissipated there, can travel, diffuse into the solid, as you can see. And you will get a heat-affected zone with all the problems of melting, deforming, splashing, and so on. And if you go to the short pulses, then you're reducing these zones and side reactions. Just for the beginning, let's leave it that way.
Something a little bit easier to grok, you know. But the point being that you know, it doesn't deform the material, and the atoms are hit so quickly, so powerfully that they're in essence pulverized. You know, pulverized quite beyond what even sending something into a normal plasma would do, right? So it just didn't make sense to me that that it should be able to create a black. right? A really very deep and very perfect black. That didn't make too much sense to me, but you know, when you hear Dr. Para kind of skirt around the edges of, you know, what's really going on there, I think that might speak to so a lot of what Sal Pays talks about, and that is, you know, this is like machining the superforce. I think we might actually be blasting apart the atoms and maybe enriching the surface, sort of like a condensed matter physics. And that's my hypothesis, but even that part doesn't need to be real or actualized or what's going on, right? The more interesting part is that the surface area on the capacitor, and what really pushed me forward to put this forward, because a long time ago, this was like something that I came up with and I told almost nobody about. And I wanted to be the first person to put this into a capacitor. I wanted to make the new generation of ultra capacitors that was even above and beyond anything anybody had ever done before. And I thought this was the way to do it.
It should be okay.
Yeah, yeah, maybe, yeah, right. But I think there's actually a little bit more going on there. I think there's a little bit more going on there. But seeing Mr. Bueller Dr. Bueller talk about
I filled it up.
The Biefield-Brown effect actually works. You know, that he was able to get you know, the effect that he was able to actually make one that, you know, could levitate, and that that he had done it in a vacuum, and that it wasn't a lifter effect, right? It was not a lifter effect, that it's actually a real effect. I was like, well, you know, he's working with normal materials. He should have this. He should be following this line of inquiry, because this is probably the way towards treating his plates with this. Is probably the way towards creating such an enormous asymmetry that he's going to get his, you know, something usable, something commercially viable. And that's why I had to come forward and say something about it. And even to this day, they barely got to, there's another interesting thing I was going to point out, is that they barely got to using this for absorbing sunlight, but they're doing it with metal. So they're doing it with metal, and the obvious problem being, and the reason why, in fact, I could show that video if we don't mind.
Yeah. How long do you think it'll? Yeah. Yeah. No, I think that's good.
Okay. Here, let me get that one. Nope, I will get some points. There we go. Another use for his work was creating super hydrophobic and super hydrophilic surfaces, where the water, you know, water literally travels up against gravity. Also interesting. Also interesting. That's just a piece of metal. Look at the difference in the surface. There's no shine on that surface. All right, so now it's great. They're starting to get there, I think, right? You know, where I was back in 2006 when I first saw his work. But there is one thing he's missing, and it normally got also shaken loose by let's see, what's his name? Jensen Huang. the CEO of NVIDIA, was just recently giving a talk about their new GPU that they're going to be using to drive AI, right? And it's obliquely related, but the part of his speech that was very important is that they had found a way to seam two pieces of silicon, two dies together. And the reason why Dr. Guo is using metal there instead of a semiconductor is because if you think about it, what the challenge of taking a photovoltaic cell that's already doped with doped and trying to treat it with this effect, even though it is so fast that it barely has time to react, but you're talking about photons, and photons can do squirrely things, right? We all know that they can do squirrely things. So it doesn't seem practical to actually treat an already doped piece, but if you can treat two pieces separately and then you can seam them together, you can actually make this happen. And you're starting to get probably solar panels in the 80 to 90% effective range. And that's probably something more immediately useful. But I think getting off the planet's a little bit more important. But that's worth it too. That's something I think is worth it too. All right, that's what I had.
Awesome. Well, Jacob, thank you, man. That was a lot. That was a lot. So thank you.
Yeah.
Thank you very much. And so we have a couple of hands raised, and let me stop your screen share really quick. Okay. And let me see. And then Jeremiah, you had a question, or did you have you have a question, comment?
Like change screens. There we go. There we go. I got myself unmuted. It was changing from the full screen view into the full display, and it doesn't let me unmute. Well, it takes about 4 seconds to do that because the computer is really overloaded. That's why I'm sorry I don't have my cam on. I wanted to mention about what we've just seen there. It's a really fantastic new approach to technology because we've previously dealt with a fantastic metamaterial called metallic glass. And metallic glass has just absolutely amazing properties. Like its Q factor for resonance and vibration are absolutely incredible. Right now, people like Jared and Charlie are playing around with aluminum, trying to get a high Q factor for edge vibrations and general resonance modes. But if you look at something like metallic glass, they have a demo video where
this does work on optical materials. It does.
Yeah, it does. Absolutely.
Dr. Rick Perry's video, he mentions it. It does work on optical materials. In fact, it will even work on air. It's just what it's tuned to.
Yeah, and what you presented today, Jacob, was actually genius because I've recently seen a series of videos where they show you the results of their technology and they're trying to sell you these machines that can do it, right? It's laser treatment of the surface that produces an extra hard surface up to 5 times or more hard than the general material. And why? It follows the same principles of the metallic glass, right? It makes it so hot so quickly that its thermal disassociation cannot allow the material, the metal lattice, to reform a crystalline structure. So it gets into a glass state. And in that state, the random distribution of any kind of vectored force that hits the surface or anything that would deform it gets distributed in all these directions very, very evenly. So we don't get shearing or torsion, snapping, or anything like this, no deformations. And it happens so quickly that it doesn't even have a chance to deform the rest of the material.
Yep.
So it's a brilliant view, and I haven't seen that side of it. I wanted to know how it worked, and I couldn't find anything. So
I've been sitting on this for so many years.
Why is it important, though, is the question for APEC here. And we want to build these advanced craft that can go into space and have incredibly strong mechanical properties. This is a technique that you just presented where if we're trying to build these materials, whether we're trying to treat nanoscale surfaces like those which you showed changing color, which are done because the physical material is such a thin plating, right, that you can physically change it. Like we've already seen laser ablation on gold, converting a gold bar into
like case hardening gun components. Right. It's like case hardening gun components, except with a laser. Yeah.
Right. So we've already seen laser ablation in a liquid solution to treat materials and change their color, or to produce nanoparticle or surface ablations that have a certain pore size. So that stuff is recognized, and it all really makes sense. It's just a technology that's been overlooked for decades, really. And what he's showing here is like a properly done setup. where we know we can change the surface structure of these materials, especially for a spacecraft or the surfaces of our plates for extremely hot, like let's say we wanted to turn a physical copper plate, just the surface of that copper plate, into something that had 100 times the surface area, but it didn't get any bigger. This technology with that nanosurface allows us to create 100 times that surface area. And in battery technology, of course, that works, but also in asymmetry for capacitors, for high voltage asymmetrical thrusters.
Precisely. Yeah, that's why I had to come forward with, because if you want it to be asymmetric, this is going to get it as asymmetric as we can theoretically can get it right there. That's the way. That's the
and the most fantastic part is you don't require any kind of super advanced materials or ultra technical processes. This could be literally treated right on the spot under an argon atmosphere with no oxidization, and then right there on
in fact, the price on these lasers has been coming down significantly on the fiber channel TI Sapphire ones. It's coming down significantly. It's almost within the reach of even a private researcher like me. It's almost there. Which I wonder why they have been coming down with the price of it so much. I wonder why. I don't know. I wonder why you wouldn't talk about it. I don't know. But yeah.
Well, I wouldn't say it's that hidden. YouTube has fed me through the algorithmic computation. They're running there several videos related directly to this technology and left me wondering, which your presentation today answered all of my questions about how that tech works. So that was awesome, but YouTube is already feeding it to me, so it must be getting out there in some capacity.
I think it is. But I think it's being seeded at the moment. I think it's in the seed phase, and that they haven't gone with the, they haven't prime-timed it yet. Honestly, if you ask me my opinion, I think this was known probably a long time ago. I think, but way before Dr. Graif put it out. I think it was in the labs of Brown, probably. They probably already knew. We just they got to trickle it out because they got to get things moving forward. But anyway, this stuff, it's exciting.
Awesome. Okay, well, thank you. So I'll go back to Jared. Jared, go for it, sir.
Jacob, outstanding presentation. I loved it. A couple of comments. You might find some good hidden useful gems amongst UFO accounts with relationship to what you're talking about. A few examples. So MUFON case 74282 was a famous one where this guy who was like a DOD contractor went out hunting. He saw a big giant ship that was pretty close to the ground, had a bunch of colored lights going around the outside, and it was shaped like a barbell. So that case is called the barbell case. Anyways, he ended up observing with his eyes that the light coming off the craft looks salty to his eyes. Turns out one of the PhDs that this guy had was in optics and lasers. So he went back, he ended up making about a dozen different patents based upon his observations of what this craft was doing. Some of the things that he noted, because he recorded it with his camera, but his camera had too much interference, but he was able to use the data that was collected from the camera to split the channels and look at the channels and see information encoded within the laser light coming off the craft. That was one of the patents he got. Anyways, so that's an example of laser light coming off of a craft for some purpose, right? Then we can go into about a half a dozen other cases where witnesses who are like in their car or out in the field or something, they feel like they're getting hit by a light coming from the craft. The color of the light is often either white or bright white blue, which based off your thing, based off what I was just doing a cursory glance around, that looks like that was the chemical non-ablative looking kind of thing, or semi-ablative. So and those lights that people get hit with, they get hit for a few minutes and then the light goes away and the craft goes away. It's almost like they're getting scanned, right? So another application.
Well, Dr. Pero actually talks about using it for metrology and everything like that. So he does talk about that there are ways that you can use the effect non-destructively for metrology and for scanning. And he even in particular talks about scanning the inside of an engine to be able to pick out the reactor species, so that they can tell at which stage they have what thing being produced as it goes through the cycle, so that they know how efficiently they're getting the cycle to run. So yeah, no, that jives actually. That does jive.
Yeah, using
Do you know the case number for that one?
I don't know the cases for the laser light like being used as a sensor. I might be able to go back through and find it. There's even some videos of that happening too, and some of the videos are a trip. You got to take it all with a grain of salt.
Oh yeah,
obviously. But some of these videos, the light isn't going in a straight line. You can tell that the light is salty, that it's a laser, but it's got a curve to it, almost as if they have like a helical constructive interference going on. So like part of the wavelength isn't visible. And then, you know, they have like
you gotta watch that video. You'll love his talk on frequency cones. You'll love it. You'll love it.
So the third and last example I have is Ted Phillips, who was like the world's master UFO trace case landing studies guy that worked with Project Blue Book. Ted Phillips did a bunch of soil samples. He investigated over 10,000 landing sites himself. And he did on a ton of these, the ground underneath where the craft landed is desiccated and it won't allow any water to penetrate the soil, right? For like a really long time afterwards. They even did some chemical analysis afterwards. It looked like there was a added amount of like some silicon boride casing, or there was like some added casing around it. And they said that casing was responsible for the desiccating nature of it. But based off your talk, I'm just like, riffing here. I wonder if maybe they're utilizing some of these lasers in part of their propulsion in some way.
Well, there would be some interesting effects, definitely, because as he talks about, when you get relativistic, you know, with not just the electrons, but with, you know, you're getting relativistic with, you know, the ions. What happens there? You know, what's going on? You know, I mean, you know, how do we enrich things, right? You know, so. Yeah, I'm going to link
put your email in
his
the
full
chat.
talk here. 1 second. I'll link his full talk for everybody. No.
And just to finish that out, also there's often, you know, remnant radiation occurring off of the soil after the landing type thing. But
that's awesome. He talks about the well, I mean, you know, every laser, right? At some point, that's just part of it. But the extremes that some of these tabletop systems can generate, that you just don't want to be directly around them. There's his full talk right there.
Awesome. Thank you.
Definitely want to check that out.
So just to finish that thought out with the landing cases. So this idea, though, that you can have hydrophilic surfaces being created from whatever energy is coming out from underneath the craft is definitely something that you should look into, is Ted Phillips trace case landings and desiccated soils.
Absolutely. Yeah, I'm going to take,
you might be able to.
You know, I'm not going to say that I think that they recovered craft, you know, except that, you know, you now have, you know,
there's no potatoes.
Yeah, right. Well, I mean, you've got Grush going out and talking about it and everything like that.
You're kidding.
Oh, hold on. Sorry about that. Okay.
Well, okay, well, because I don't have the primary data.
I was trying to keep time of it right here.
Royals,
I'm with you.
Yourself.
Just listen.
There we go. Sorry about that. Okay, got it.
So I don't have the primary data, right? I only believe, you know, what I can see, right? But you know, if you ask me to bet on it, I'm betting yes. If you ask me to bet on it, I'd put money on it.
Bill Uhouse came out and said that the simulator craft that he was a test pilot for and a trainer for came from the Kingman crash. And the Kingman crash has been mentioned by a couple other high ranker people as of late as well.
Yeah. I mean, I'd put money on it. If I were betting, I'd put money on it.
Yeah.
These things are just, they're too out there.
Well, and so if I could speak to the UFO thing, APEC is not, again, like for anybody who's kind of new to it, APEC has kind of picked up and absorbed like 4 or 5 different kind of micro communities, right? And so we are not necessarily, you know, like not everybody here believes in UFOs, not everybody here is into UFOs, but like if you did a quick survey, like most people probably do. So that's kind of how it shakes out. So, you know, I'm just putting that out there. What like so it's one of those things. Some people are pro, some people
How
are
about we
against.
do a reverse survey and ask if anyone doesn't believe in UFOs?
Yeah. Okay. Here, let me put it on. Let's do that. I'll put it on gallery view. Okay. So if you do not believe in UFOs, you got to turn your camera on and raise your hand. There's one person.
Oh, we got one person.
And he's smiling.
Bill Alec has a gun up. Okay, we got Sharish.
Okay, we've got
Erickson.
Shrish.
What about if you're agnostic about it?
Then it's kind of a wave.
Yeah. I don't know, like a half hand wave, like half hand raise, like.
I've reached the point where my brain hurts. I don't even know what the symbol for that is. Like, so, yeah. So I think most people, right? Like, you know, I think everyone would agree that something is going on. It's what that something is that nobody's sure about. So
Let's get out there. Let's go and find out. Right. Let's treat some of Dr. Bueller's his examples, some of his best examples, his best designs, and see what happens. And let's go find out.
Already did it.
Let's go find out.
We've already done it.
Yeah.
Yeah.
So I have this theory about UAPs as being an elaborate hoax, a hologram, just so that DoD can get more funding. No one agrees with me, but
They could crash airplanes into buildings in order to get more funding. They don't get funding from that.
Happens.
Or it could be to distract
casualties
us.
of war.
It could be to distract us from their funding. That could be the other.
Somehow they had holograms though back in the 40s.
Yeah.
Yeah.
Probabilistically, I think they must have aliens, but logically, if aliens are that smart, why didn't they invent like bioengineered robot to conquer the whole universe?
Yeah. That's what we are.
Yeah.
We are the bioengineered robots.
The most fundamental thing is we always see this UAP phenomena in Earth, so to say. If they're really from alien space, how come no satellite has ever spotted them coming through space?
Oh, there's plenty of that.
Space is big. It's dark, and they're not looking for them.
There are
Actually,
a lot of space videos with unidentified.
Actually, yeah,
a lot of them.
I can speak to that briefly. I've done a ton of defense interviews, and so right now, and this isn't UFO based, but right now there is what they call a Cold War going on in space, primarily between the U.S. and China, right? And one of the things that our defense folks have had trouble with is basically like it is so big and so dark and we have so little awareness of what's going on there that, you know, when something bad happens, right, like one satellite tags another or something like that, they aren't even sure who's doing what sometimes. And to me, that was kind of a surprise. So I that would kind of go with what Mark and Jeremiah were just saying. Our awareness is not that good, surprisingly. You'd think it would be better, but
yeah, I agree. It's just too vast, really speaking, to monitor everything possible, kind of thing. Yeah.
Well, and I'm not saying that UFOs exist. Again, it's, you know, it's a personal belief. Oh God, we've made it to that point.
Well, okay, so then you've got these other programs. I'm sorry to butt in here, and I've got to just at least mention this. You've got these other programs where you can easily assemble your own device to spot these things in the sky in just about any clear night at many locations where you don't have basically too much light pollution. So you just get away from the city a little bit, point this type of camera in the sky, and you're looking in the very short wavelength infrared. Only certain types of night vision cameras have the ability to view it. And then there are certain lens setups to help enhance the product of your recordings. But you'll look at these things and you need extremely high frame rate. So here's the catch. A lot of the stuff is invisible in the skies because it moves way too fast. Which is no surprise because these guys aren't really dealing with the same problems of inertia that we're dealing with on our low-level Earth-based technology, right? They can accelerate insanely fast and they can fly by insanely fast and change directions quickly. So you need an ultra-high frame rate to capture that kind of stuff, and most cameras just can't pick it up. And our eyes, we're not going to see it. So there are ways to pick it up. And I'm just saying, like, if somebody really wondered, are there craft in the sky that we're not aware of? Well, you've got to set yourself up with a rather expensive camera and look at the slowed down video information after you've recorded it. That is recording in the very, like I said, the very, I should have said ultra long wavelength. I said short wavelength in the beginning. I apologize for that. I meant ultra long wavelength infrared. So there you're talking about things like thermal cameras, basically, that are operating like your point and shoot laser thermometers. Those are going to operate in a really long wavelengths. And if you look at the lens on those, it doesn't even look like a lens. It looks like a piece of white plastic, like a milk jug. But it's a lens for that wavelength, so that can see it.
And the other thing that's worth pointing out is that when our dear, wonderful government decided to reset their sensors to actually pick up UFOs, like last February, right? They suddenly found this fleet of Chinese spy balloons flying overhead, carrying like these double school bus sized payloads of cameras, and so my trust in government is somewhat eroded. We'll put it like that.
Okay, if I could say something, I have some information relating that. I met this guy who is called David Whitey, and his father used to be one of top ranking officers in NORAD in Cheyenne Mountains in Colorado. And they have this, NORAD works together with Canada, and they have this large system of radars which tracks everything up to geostationary orbit. And when I say everything, everything down to the size of a football. So it's not true that we couldn't see them. We could see every single one UFO as it is coming in. So what's actually happening, as soon as they spot UFOs, they zoom in cameras from the ground or from the satellites, and they track them, and they get exactly their trajectory, and they could predict where these UFOs will land or head. And then apparently, according to some information that comes from YouTube and from soldiers who were serving in these units, NATO Pact has 4 teams. I think one team is based in United Kingdom. 2 teams are based in North America, and 1 team is in Germany, I think. And when NORAD predicts these flight paths of UFOs, they send teams over there and they secure landing sites in basically to isolate it from general public. So these things are and David said that approximately there is one large sighting per month of these UFOs coming. And there is a certain pattern of the way they come in, because the pattern is related to position of the moon. I forgot how it exactly works, but they basically use moon to brake when they are coming, and then they use moon to assist them when they are leaving. So there is a monthly seasonal pattern to when they are coming in and out. But that information is maybe 20 years old, because since then David's father retired and stuff, so he's out of touch. But these things are definitely tracked by NORAD, but they won't tell you about it, or they won't speak about it publicly.
Okay.
Dejan and Tim, I have some firsthand stuff on that you both might find interesting. So over here on the west coast of the United States, there's an Air National Guard base out of Oregon that ends up doing the whole west coast. It's like West Coast Defense, right? And those guys, they have a couple of jets that are always ready to go at a moment's notice, right? And so if anybody like goes into the wrong airspace, those jets are there in like a minute, right? But what I wanted to say was that those jets, I fixed the avionics on those jets for 11 years. And those jets, what would happen is they would get scrambled at 10 p.m., 2 a.m., whatever, right? They get scrambled for, secret reasons. We don't know why they're getting scrambled, but I would hear from the crew chiefs that worked with the scramble pilots, the alert pilots, where the planes went, not what they were doing, but where they went. And one place that they always go, similar area where they often train, is just off of the coast of Astoria, Oregon, which is like the very northern corner of Oregon next to the ocean, right? And when you look at UFO hotspot maps, that happens to be an UFO hotspot area. What's more, not all the time, but occasionally, those radar systems in those jets would break down in one way or another. And so they'd come back and they'd say, hey, something wasn't working right. But sometimes I'd have to say, as a back of the napkin, ballpark, about a quarter of the time, there would be nothing wrong with the radar. And the specific write-up on the radar was birds or static or noise on the radar. But I was the guy who was testing that. And I was absolutely certain, no, there was absolutely nothing wrong with any of your radar systems. Whatever you saw on your screen, that wasn't a problem with your system. That was something that you were picking up. And the birds, the noise, the static they were talking about, it was just like the whole famous video of, there's a whole fleet of them. Look on the SA, right? That fleet of them, that's a noise, that's birds, that's a bunch of like targets on your radar that if somebody with access went through the maintenance records that are totally digitized now, if somebody went through the maintenance records and filtered out all of the repeat serial number offenders for the systems and only took the first time offenders and happened to look at the dates and times for those things and could go talk to the pilots who are writing these up, they might end up finding out that the pilots who were writing them up were too scared to come forward with what they actually saw with their eyes and were just trying to convince themselves, no, I hallucinated. It was just, some noise on the radar. That was all I wanted to share on that.
Yeah. I guess we need to find out what's the difference between what they saw and like something like a hologram or a laser light show, really speaking, something really advanced, more than what we get from Hollywood kind of thing.
Well, Ryan Graves, who Tim mentioned earlier, he mentioned how his wingman, his other pilots that he was flying with, like that these aircraft, these saucers, whatever they were, that they were coming up within single-digit feet of the plane. Sometimes they would sit right in front of the cockpit and make it so you couldn't see where you were going, right? And you would try to dodge and the thing just is locked with you, or it'd sit right on the wingtip. And those are just the cases where nothing happened. There's cases from the 70s where planes were actually damaged from colliding with these. And those are like the old public knowledge ones. There's ones they're trying to get declassified now where supposedly the aircraft were actually damaged to the point where pilots had to eject. Like they're taking out, $40-50 million assets. And
you mean like as if like something physical hit them?
As in the fighter pilot couldn't get away and accidentally, not intentionally, but accidentally, the pilot's craft and the UFO collided in a way where the pilot had to ditch the airplane. And when you ditch an airplane, you lose the plane. And those planes, they're expensive. And if the military loses a plane, they're going to write it up as some other reason why he had to, he got discombobulated and, he was upside down and he pulled up instead of down or something like that.
Yeah.
Yeah. Well, yeah, let me go to Drew. Sorry about that. Brad just mentioned that in chat. Actually, I was saying, let's go to Drew and then I was muted. So Drew, go for it, sir.
Yeah, hi. First, I just wanted to mention that if you increase the surface area of a plate that Dr. Bueller would work on, because I'm the guy who builds them for him, so it doesn't do any good. You can sandblast or chemical etch the materials, and you will increase the effective surface area, but because it's electrostatic in nature, you're not effectively increasing the surface area that the electrostatic pressure is operating over. So it doesn't do any good to laser ablate, although that's the coolest thing I've ever seen, where you laser ablate a surface and change its color. I'm working on that with one of the guys who invented the femto laser on a whole nother project. So that's the first thing I just want to mention. And secondly, I've been in a previous life, I did serious deep sky astrophotography for about 15 years. And I've got some pictures if anybody wants to see them. Can I throw them up, Tim, or we?
Yeah, no, go for it. Go for it.
Okay,
Yeah,
I'm
run
gonna try
run
and
through those
figure
real
out
quick. Actually, I'm going to
where
mute
this-
myself out and I'm going to run for just a moment. We'll be right back.
Trying to find the screen. I'm
There we go.
guessing that's, I don't know what this is. I hate technology and it hates me back. Don't know how to, okay, let me just get rid of that thing. All right.
We see you with your telescope right now.
Yeah, we
This
see
is-
you with your telescope.
I'm
and
not
gonna-
kidding you guys. I spent enough money. That is a 0.8 meter f 1.04 primary mirror, okay, that I custom built. And that is a fully robotic telescope. That thing went out under the stars every night for about 10 years. And in all of that, the tens of thousands of frames that I took with that, this is a state-of-the-art apogee camera sitting down here on the bottom of this thing. Absolutely state-of-the-art. Had a sensor on it about 2 inches on a side. In the tens of thousands of frames that I took, the only cool thing that I can say I did not understand was this one. Something was zipping through the Eagle Nebula at 1 o'clock in the morning. And hang on, I'm trying to, I had a better picture of this. Yeah, there we go. Okay, this is when because I used to do multi-level imaging, red, green, blue, and many different filters. So I stacked it all up, and then I super contrast enhanced this. This is the only thing I couldn't figure out in tens of thousands of photographs of the sky was, I don't know what this was. And this is my one and only, I don't know what this is. Could have been a meteor, could have been a mothership. I don't know, but I know the guy who took it, and I know he wasn't BSing. So take it for what it's worth. I looked at the sky nonstop for the better part of 10 years. And I had equipment that is absolutely state of the art. And I never saw anything that I couldn't explain except this. And somebody told me this was a meteor that I got really lucky and captured while the head was still right there at the instant that it happened. But that's really unlikely because this camera, this was a multi-minute exposure. So I don't understand how that would have happened. But anyhow, that's it. That's all I got.
Hey Drew, so I happen to do a lot of EAA, what's called EAA nowadays, which is live viewing, and do it, with others online. And I've seen in those type of things where, you see something going through, and often it's easy to identify satellites because they're streaks, they're moving so fast. But when it's those exposures are maybe like in the tens of seconds and they're stacked, right? Because you were trying to get deep. and you know, you see something kind of slowly moving off, it's really difficult to try to identify what it was. So we had tried to follow there was one object I'll never forget, I forget which galaxy we were looking at, but it was through a 14-inch, about f2 f3 scope. This fellow who was in Northern California, he would use all the time in broadcast, and you know, mainly for broadcasting galaxies live. And we saw something moving, and he started, you know, kind of trying to follow it. We got a few images, and we went and tried, you know, a bunch of us tried to go and find out, okay, was this something that's known? Maybe it's a comet or some near Earth object passing through. And it's really tricky to go out there and find that stuff, because you know, unless you can predict where things are, it's hard to you know, take a single image or even multiple images from past dates. But I'd be curious if you had that image, if you know, like, when it was taken. You know, maybe someone can look into whether there were surveys or other observations of the similar that same area of the sky, seeing if there's other observations of that.
Well, I ran it down with a guy who has 10,000 near Earth objects to his credit. Some dude out of Southern Illinois, and we chased it down, and he's like, it ain't in the catalogs.
Yeah.
It was one of those fluke things. It was probably a meteor, but
yeah,
if it was the coolest looking meteor I've ever seen. And I've seen a bunch of them.
Yeah, I actually got a picture of like what's landed in the backyard, but I'm not quite too sure what it is, if it's an orb or a spaceship. But I got pictures of it in a video if you would like to see it.
I would.
You would?
Sure.
Yeah.
Yeah. I'll share. I see. I've already sent this to Mr. Michael Boyd, and I don't know what he thinks about it, but I don't think it's anything inside the house that is reflected through against the window, but I think it's morely outside, because that night as well, I kind of spotted a gray alien as well at the back. I saw its torso, and that's about it. But I'll share it with you. So I'll see what you think about it.
Okay. Well, let me see. Let me go to Jeremiah, if that's okay.
Yeah, I just wanted to mention one thing before we jump off and take a look at those pictures that he's going to share. So, Drew, in gentle opposition to what you were presenting, your opinion about laser ablation and its effectiveness in creating extremely high field gradients, I just wanted to mention that these gradients may not appear in a DC or static system like what you're testing. So I understand why you probably have a bias towards that. But under alternating fields, or any kind of volt per meter change over time, right? You're going to deal with these types of enhancements from that extremely high surface area and deformation. So just take a look at the work of Richard Van Duyck, where you're looking at motional electric fields that you can trace back to a few other sources, and then forget about the gauge out factor that we have in the refractive index, and consider a gauge-free approach where we understand the refractive index is nonlinear and variable or polarizable, aka the vacuum, right? So these things can operate because you can change the intensity of the electric field and its polarization over some period of time, or you can add a DC bias to create a continuous polarization in the gradient field, and then fluctuate that with an AC signal injected on top of your DC bias. So I understand that's not what you guys are doing, that, you know, you found a way to do it basically with virtually no losses with DC, but consider the other options that you can do this dynamically as well with the pumped source.
But you're saying it doesn't work with DC at all, Drew?
It doesn't have any effect.
No.
In fact, the smoother the surface, the better, but that's just from a electrostatics perspective. But it's very interesting. So you're saying that when you run AC at a high enough frequency, you're basically running the energy over the surface. It has almost no skin penetration. So there's like no depth into the antenna. It's like all the energy of an antenna is on the outside
Means
surface.
basically this. I can explain it in a way that I think will you can visualize things, right? Yeah.
Sure.
Okay. Well,
Frequency has
anyway,
dimensions.
just imagine this: you have trap charges or bound charges that are now moving from your electrode plate that has an extremely high surface area to the nearby surface of your dielectric, and then you have this other really smooth plate on the opposite side. What's going to happen is when you have an electric field that is operating at a high potential, your bound charges are going to try to migrate up to the tips of all those fine little points for your nano surface. And so they'll be really, really concentrated there, creating extremely high field gradients right at the surface of your nanostructured or laser treated material. Then on top of that, you have this dielectric field that's being produced in the field gradient through the dielectric material, which preferably you have a lossless material that can operate at really high frequencies. Teflon, for example, would be one solution that will operate at high frequencies. You pump a really high frequency voltmeter and get the fastest transition that you can. If you could drive square wave, that would be ideal, into the plate with the high surface area. What happens is the surface charges that are at the very tips of each individual nanostructure, they could be spherical or they could be sharp points, they'll oscillate up and down and move at extremely fast speeds. And they produce a linear electric field gradient that's geometrically amplified because they're moving up and down just like an antenna. So from the sides, you have a transverse wave. From the tips and from the base, you have a longitudinal wave. This oscillation changes the relativistic momentum of those charged particles that are moving up and down, your electrons that are in this metallic nanostructure. They, because they are oscillating at a really high frequency and a really high speed over a really short distance, have a different gravitational coupling coefficient to stuff from the side, that mass is located around the side, versus mass is located in the front or the back. And so now the electric field polarization actually does play a role, because now your electric field polarization following that gradient is going to have a really extreme vector momentum that's going to be spreading out in just one particular direction. And that creates an unbalanced gravitational equivalent field because of the stress in your energy momentum tensor.
Like ripples in a pond.
Exactly.
Yeah, would you like to see the pictures now?
Pictures?
Yeah, the
Yeah.
pictures in the video.
Yeah, go for it.
Yeah, I'll load it up. So I've circled the image of what I think is an orbital some sort, but I'm not quite too sure what it is. Can you see it?
Yes.
Can you see it?
Yeah, sort of, kind of. Although I'm
Sort
I
of,
see
kinda.
something in the mirror, like
Ghost?
something in.
Yeah, but there's nothing reflecting it because I got nothing inside that resembles it at all. And it's more overly shaped. And there's some sort of a center.
Like a ceiling light.
No, that's not a
looks
ceiling
like
light. The ceiling light you can see. The ceiling lights is up above, but that is totally different. But I'll show you the video. I'll show you the video. Hold on a tick. I'm just looking for it.
Yeah, I think we're good for a couple minutes while you search for it.
Yeah. I would love to have a conversation with anybody that wants to talk about RF being pumped through that magical stuff that Linda Milan or Maloon, whatever, the little pieces of spaceship that she found.
Oh, the arts parts. Yeah, Linda Moulton Howe.
Yeah, that's it, Molten Howe. I'd love to talk to anybody that wants to have a conversation about that and pumping enough RF through that material to make it do something.
Doesn't Gary Nolan have some of that now?
I'd be willing to have that conversation.
Who's willing to have that conversation?
Can we do Curtis's presentation before we get on that?
Yeah, my
Has
video,
dimensions.
my video would actually won't share. So yeah, so that was
Okay.
it. That was just a photo.
No, that's awesome. That's awesome. Well, Doug,
Yeah.
thank you. Let me, if it's okay, Curtis, do you have updates for us?
Yeah, just a short update.
Okay, yeah, go for it, man.
So let me share my screen. Hopefully you guys can see that presentation. Get it started. Okay, is it working?
Yeah,
All right.
no, it looks great.
Okay, good. So it's only been a week, so I don't have many things to update here, but we do have a new device is in the chamber, and it's working. Jim did some updates he detuned some of our sensors so that we were getting overranging. So our graphs don't look as spectacular, but that's from the detuning. And so yeah, the device is in there. We did a couple runs before Jim left for the day, and things seem to be working a little bit slightly different, but they're working. We're still getting the same kind of push. You can see this is a picture I took of the screen, and I'm in the lab now. Actually, the lab computer is capable of joining a Zoom, so I could get in here live later on. If you guys want to see some live runs, I can turn the vacuum system back up. I have the pump off right now because it's pretty noisy. So things are working as expected. We're getting some movement there. So these are the new devices, and as always, we got to tune things up and get them going. So I can show you guys a video of the runs that we're seeing right now. Let's see here. Oh no, I had to actually stop that. Put that back in real quick. There we go. Perfect. And let's see here. I think this video should be, oh, sorry about that. It is trying to start up in parallels. I'll just open it with QuickTime. It'll work better. Okay, so that's a run that was just done maybe half an hour ago with the new device. So we're getting very similar results, and as you can see, the motion is clearly visible. We have yet to analyze it with tracker to determine, what kind of motion is it? Is it opposite motion or the same, pushing in the same way? We are seeing some of the side bands pop out. You can see that there. That was pretty prominent. So it's promising. It looks like it's working kind of as we expect. And by the way, that gold trace that you see coming across there, that's the accelerometer that's back there. So you can see that is pretty prominent there. Okay. So next, I added a couple things, or actually one item that I found recently to my physics remarks that I've been consistently giving, which adds. Actually, I found this during the last couple days. There was actual paper that was put out there in let's see, the 2012 timeframe in the American Journal of Physics about particles being the wrong idea. Basically, matter is fields, not particles. So kind of updated my presentation here with that. So there's a link on archive, and I recommend anyone trying to understand the field theory that I presented in the past, that this is probably a good paper to read to kind of get you calibrated in terms of thinking about matter fields. Okay, so one of the big problems with figuring things out in physics is deciding which ideas are the ideas that you want to explore and kind of hold that, okay, these are ideas that I'm starting from, right? Where you have a basis. And the idea of a particle and a field in this particle wave duality is something that's been a confusion and a problem from my point of view. Actually, that's what I've been thinking about. But I would highly recommend reading that paper, and I can show you guys the archive page. Basically, like I said, it was in 2012. This is a preprint, and it was published, I believe, in the American Journal of Physics. It says they're to be published, but that was published. It did go in there, so that's available on archive. And I highly recommend you guys that want to pursue this work. It's important because what we're trying to do is something that's with propulsion, trying to do something that's outside of the mainstream, right? In terms of like predictions. So really, you really want to think about, what matter really is and what we're really doing there. So I highly recommend that. And of course, I think this presentation is available, and if not, I'll make sure Tim has it. But the other things I recommended is this talk, the 6 paths to the metric tensor. Actually, I talked to Jim. He said, he's a historian, so he said he wasn't impressed, but I was I liked it because I've never sat down and gone through what Einstein's thinking was back then. So that's okay. And then of course, Carver Mead's talk from last year. I highly recommend these as ways of kind of starting to think back to like what the fundamentals are, what Einstein was doing with his field theory, and what we know now, which is with this neutron wave experiment, we have it confirmed that matter is a field or a wave. You can use those terms interchangeably maybe. And also that matter is, the Mach principle is true. Matter does know where it is in the universe. So that's something that we can't ignore, and there's experimental proof. Okay, so that's about it. Stop sharing here.
Awesome. Okay.
Tim, I had just one short question for Curtis.
Sure.
I'm just curious. I see there's in that video, it is oscillating, right? So is that what you guys are working on, trying to get it to be consistently unidirectional, or is there something else you guys are working on?
So the way we're putting energy in is through a frequency sweep. So sometimes it'll go one way and sometimes it'll go the other way. And in the in-depth theory that's been figured out for this, it is possible to thrust in either direction, depending on how you're putting energy, and the dB, the kind of the sign of the dP dt, P being power. So you can actually have it so that it pushes one way versus the other. So that's kind of what we're seeing potentially. But the other thing that we need to roll out is a kind of stick slip type thing where one's going the other way and they're just
Oh, you mean like in combination?
Yeah. So we want to rule that out. So that's something we're talking about. That's a concern of mine. Like I want to make sure that we're not, just proceeding like by ignoring that. So that's a possibility, and that's why the video is important, because with the video we can see the device and the torsion arm and how they move. If they move together or they move in opposite directions, and that kind of informs us what kind of motion we're getting.
So on that frequency sweep that you mentioned, so is that like a kind of a chirp kind of signal, or what is it?
So for example, the one I just showed you, let me take a look here. It was a 10-second sweep from 37.5 kilohertz to 32.5 kilohertz.
Okay.
So we swept over that frequency range in 10 seconds. So that's about 500 hertz a second or so, I believe.
Yeah.
And so as you go through that, you hit different resonances. and those resonances, and you can see those peak from the gold trace, which is the peak. There's one of the 8 piezoelectric discs. We don't put power in, we read the voltage from. So that's like an accelerometer, because as it gets squished, it's it's giving voltage out. So that accelerometer tells you when the disc is excited and hitting resonance. You can see that.
Okay. So it's like you're stabilizing these waveforms such that you get the DP/DT in a consistent manner. So that's where you guys are. Okay.
Yeah, and
because I was always curious.
The Mach effect comes out of the kind of the synchronous nature of the acceleration with the energy transfer. So those two things need to be present in the right timing for that Mach effect to occur per the theory.
Yeah. So that's that internal energy transfer, right?
Yeah. What we're putting in and taking out. So, yeah.
Okay. Yep. Yeah. Thanks. I was just curious. Yeah.
Okay, William, his hand up.
Oh, yeah. Can you hear me, Curtis?
Yes.
Yeah. Yeah. I think what you're saying there is correct. One of the things that Tom Bearden said, in his lectures there, was that all matter is made of light. So it's how the light is trapped to form the particle. Okay, and that shows up in quantum mechanics as well. It's the square of the frequency. And when you square the frequency of a photon, for example, you get a scalar function. Okay. And so it's basically a matter wave. So all matter, everything in front of you is made of light. And I thought that was rather interesting.
Yeah,
I thought maybe I just passed that on.
It's interesting you bring that up because there's a fellow by the name of John Williamson, and you can look up his website is Quasi-Cycle or Quantum Cycle, QUI. I put the link in the chat there. And his theory is based on that and he used to be a particle physicist, okay? Or used to be, or actually was practicing particle physics. He went to CERN, unlike me, which turned down CERN. I didn't want to waste my time, but I felt guilty about that. But I can tell that story some other time. But and I felt better after a while. But it's interesting. His theory is interesting because he takes the photon as fundamental, and the photon kind of like doing a motion. So light doing a motion is a fundamental thing. So he treats the particles as just a light kind of curving around.
Exactly. Yes.
And what I find interesting about that is that it's kind of like a mirror, almost like a imaginary or a mirror universe view from the field view, the classical field view that Einstein and Mendel Sachs had, which is fields are all you have, and the fields interact, and their interactions are one-to-one, and there's no free photon. So as when you talk to a physicist and you say, okay, I have a free field, some of the old school guys will tell you, oh, you don't have a free field unless you have a source. There has to be a source, right? So if the source is, so it's almost like, okay, well, the source is the field, it's like a circle, right? So you could have the point of view where it's all one or the other. It's kind of like almost like, okay, all energy is positive or all energy is negative, but you can't both, right? So I find that theory very interesting. I've been looking at it, hoping to talk to John about this stuff, because what he's done in that program is really interesting, in that he's have similar predictions to what particle physicists do, and but don't take their theories and their assumptions about what they're measuring as fundamental, meaning there's not some, when they make a measurement, they're still measuring electrons and positrons there's no direct measurement of some of these exotic, parts, as they call it. So it could be that those are just features of when you get higher energy, how the matter fields self-interact. Okay. So anyway,
well, you see at the macro level, if you're working with coils and magnetic material and that sort of thing, you can replicate that effect. Okay. And especially with counter rotating fields. Okay. If the fields were counter rotating, you get the scalar energy effect, time reversal, and anti-gravity. Okay. But if the fields are rotating together, okay, you have time forward, you have gravitational effects, a scalar function, and, basically a matter wave. Okay. Just from light. That's all you need. So that was a presentation I wanted to give tonight. I don't know if we have time for it, but it's up to Tim whether I can present that material or not. But it's mainly Tom Bearden's anti-gravitational system, time reversal, because you're working with reverse time. Okay, well, you're going to have anti-gravity. Oh, did you want to say something, Tim?
Yeah, I was actually I was going to have you on. So, and Bill, let me apologize. Bill's been having Zoom issues, raising his hand. So that was that. Yeah,
it seems to be working here.
Yeah, I was good. Actually, if it's okay, so we have Joe and Richard. If it's okay, let me go. I think they had questions, right? If it's okay, let me go to them, and we'll come back to you, Bill. Does that work?
Sure.
Okay. Hopefully, I'm doing okay moderating today. I'm still a little spacey from the trip,
Doing great, Tim.
Okay. Fingers crossed, please. Well,
Okay,
yeah.
Thank you very much. I just kind of been, as I said, I've just been sort of sitting in the background watching my first time, and it's a little bit much for me. So I'm just kind of digesting everything. I thought I'd throw my paper out. I don't think there's time to discuss it tonight, but maybe next time or sometime in the future, I'd be happy to do that if anybody has an interest. But thank you all very much for all of your presentations. I've enjoyed watching tonight.
Oh, well, thank you as well. Thank you as well.
Did Richard have a question?
Richard might be. Oh, Richard, okay. There we go.
Yeah, the internet's really slow. Could you hear me?
Yeah, I can. It looks like you are having some connection issues. I would say give it your best try and.
Real slow on my end.
Yeah. What might help is turning off your video if you wanted to just have a question. That might help.
There you go. I stopped his video.
Okay.
Okay. Yeah, here's a. Were you able to see that?
Oh, well,
okay.
not now. Sorry, I just stopped your video so you could speak more easily.
Okay, yeah. So did you see the graph? It's just a basic graph, right?
No, you don't have any video going right now. That way we can hear you.
Okay. Were you able to see the basic graph I held up there?
No.
Yeah, turn on your video, maybe.
Okay, let's see.
I asked him to start it again. I think the problem is we have a time delay also, right?
Mute the audio, start the video.
Well, we'll give it. We'll give it a
bad delay here.
Yeah, Richard, why don't we come back to this?
Reconnect.
Well, yeah, try and reconnect. See if you can find a better connection. Maybe get closer to your Wi-Fi if you're on that. That always causes issues. Okay. Yeah, Richard, why don't we why don't we come back to this? See if you can maybe see if
Yeah.
you can get the
Can
connection.
you? Oh, okay.
Okay. So why don't I do this then? It looks like
Try
Richard is
lowering the video resolution.
let's go to Bill Alec. Bill, do you want to do your presentation?
Okay, I think I unmuted the mic. Yeah, sure.
Okay, yeah, do that. It's 6:41. We don't have to. Usually, I go till around 8. We don't have to go that late tonight. It's up to you guys. It's a little
Okay,
bit
share
quieter.
the screen. Let's see. Okay. Okay. Can you see that? Can you see the screen here?
Yeah.
Okay. Let me put this on slideshow. From the beginning. Okay. I don't know, can you see the main screen here?
Yeah, it's visible. Working good.
Okay. All right. Okay, the presentation here it's mainly on Tom Bearden's technology, and it only took me 20 years to figure it out. Only because Tom is a great speaker. Okay, if you see any of his videos, watch his videos, his presentations are fantastic. But there's a catch to it, and that is he would leave certain things out. And that's what you try to wrap your brain around, is what exactly is this guy talking about or speaking about in his lectures? And so it took me a while to kind of piece it all together. And that's what this presentation here is about. So let's get into it here. Next slide. Okay. Free energy. You spoke about free energy, anti-gravity, time reversal. They're easy to do. You don't need tensors or different diffie-qs. You don't need any of that kind of higher math. You can do it with high school science. And that's key point number one. Key point number two is that the zero vector is not zero. And you have to keep that in mind when you're working with this kind of technology, and especially with anti-gravity or devices that display anti-gravitational effects, because you're working with negative time. Time is running backwards. To do anti-gravity, time has to run backwards. And you have this free energy effect, which is really the scalar waveform. And I'll get into that a little later here. Okay, so the next slide. Okay, my personal timeline. Back in '77, while attending IIT Chicago, it's an engineering school, I was given a vision, and it was just fantastic. Here I am building or constructing a disk. I had no idea how it worked or any sort of things like that. And so I passed this by a friend of mine, and she had very unique psychic abilities. And she saw the vision. And she says, "Boy, that's a beautiful looking craft you're working on." She says, "Okay." And so to me, that was verification that this dream vision was real. Okay, so back in 1979, I graduated with the BSEE degree and began my professional career. And then in 1997, I attended a Tom Bearden conference. And Tom Bearden spoke about free energy and anti-gravity. And the host of this conference was, of course, Richard Hoagland. He's famous for the face on Mars, which we don't really hear much about these days. And so I attended the conference, and basically 2 words: pay attention. Okay. And I said, all right, I'll pay attention. And so now, about 20 years later, here I am talking about Tom's technology. So I had enough time to kind of fill in all the blanks, replicate his work, find out what a scalar wave is, and how to replicate that. So what I'm presenting tonight is essentially real technology. You can replicate this at home yourself if you wanted to do it. So next slide. Tom. Okay, Tom, his quotes in these lectures, he says that all matter, this goes back to what Curtis was speaking about, all matter is made of trapped electromagnetic energy, which personally I thought it was curious, until I started seeing some of this work in quantum mechanics. The second thing he said is we can't see the dimension of time, but we know time exists because of spatial displacement. And the third thing that Tom spoke about was, of course, Oliver Heaviside. Okay, and this guy, Tom would say that Oliver threw the baby out with the bathwater. So who was Oliver Heaviside? Okay, so the thing about Tom, though, is that he wanted a big DARPA contract, for his scalar technology. It never happened. Why? Well, because they're already doing it at Area 51 S4. They're already working with scalar technology there. So what exactly are they doing? Okay, well, here's a famous quote. I'm sure all of you have heard of this from Ben Rich. We already have a means to travel among the stars. They already have this tech, okay? But it's locked up in all their black projects. And it would take an act of God to ever get that technology out to benefit humanity. And my quote is, well, I think God is starting to act. So we're starting to figure this stuff out. Next slide. So why isn't free energy, anti-gravity, time reversal being taught in our schools today? Well, let's find out. Okay, we go to the original work by James Clerk Maxwell. He was the one who published his 20 equations with 20 variables on electromagnetism and using quaternion algebra, which is very interesting. And he made his electromagnetic potential the centerpiece of his theory. So right there we had some electromagnetic theory. And then this guy comes along, this Oliver Heaviside. He's self-taught English. He invented a new technique for solving these Diffie-Qs, okay? He rewrote and simplified 20 Maxwell equations into 4 equations. And this is what they teach in every university, I would say, on this planet. And I remember seeing this in class myself. And he made Maxwell's zero vector. Now, this is very important. He made the zero vector. And what is a zero vector? Well, this occurs when you have 2 opposing vectors. What do they sum up to? Well, 0, right? Well, that's what Oliver Heaviside said. So next thing, well, these are the equations that they teach in all the universities. This is essentially the Heaviside Maxwell equations. Okay, so the reason why the zero vector is not 0 now this is very important, is because the scalar term appears, okay, with this cross product. When you take the cross product of opposing magnetic fields, for example, the scalar term appears. So it must be operated in resonance. So this cancellation process that occurs here must be operated in resonance, and you get this scalar term that appears. And so this is the mathematics that Tom presented in a lot of his lectures. He shows the Heaviside Maxwell electromagnetics, where you take the cross product of these opposing vectors, and you have the zero vector. Now, what Heaviside did is that he set this zero vector equal to 0, game over. That's it. You go no further. And that's why we don't have anti-gravity being taught in any school curriculum. And it'll never be taught because of this right here. And so what did original Maxwell equations came up with here? So of course the quaternion solution. And Tom worked out all the equations here, and then lo and behold, the scalar entity comes up. It's right there. And that's your sine squared term plus the zero vector. And then inside the zero vector, you had the scalar anti-gravitational longitudinal function. And Tom called it your vacuum engine. And then, of course, you see the sine squared term, a squared times the sine squared term. You have your two sine waves. And first of all, you say, well, where does the energy go? The energy has to go somewhere. And this is where it goes. This is your sine squared term. And that's your scalar wave. And so in this particular configuration, since the vectors are opposing, the EM wave is going to be time reversed. So it's going to improve the efficiency of your system. And that efficiency can go well over 100%. 100% is no longer a limit on your scalar function, because the wave is time reversed, and your vacuum engine is what's making the anti-gravitational component, okay? It produces this anti-gravitational longitudinal wave. So next slide. So the scalar wave term can be very, very large. And in cases like Stanley Myers, for example, burn water, not gasoline, in his engines, they produced a scalar wave function. He had an efficiency of well over 1,700%. And then when you look at Floyd Sweet's device, and Tom spoke quite a bit about the Floyd Sweet device, he had his opposing coil configuration, and he had gains of like 1,000,000 to 1. So a milliwatt put in, he had kilowatts coming out. So it depends upon the input fields that have to be matched. These fields have to be matched to get those kind of gains. Okay, so the next slide here. So according to Tom, his analysis, the two types of scalar waves that are produced is a time-reversed transverse EM wave, and also a time-reversed gravitational wave or anti-gravitational waves. So these devices, they would get lighter. They wouldn't get heavier. So the next slide. And then Oliver Heaviside came along in the 1880s, okay, and messed this all up. And so today, there's no way you can do anti-gravity in any university. Being taught here using the Heaviside equations, because the zero vector is 0. But here, if you stuck with the Maxwell equations, you find out that the zero vector is not zero. And this, and I've proven this in my experiments here. So Tom came along and said, well, Oliver Heaviside threw the baby out with the bathwater. And what I'm saying is this is the main reason why we don't have Star Trek today. Okay. Next slide. How do you determine resonance? Well, this is the coil capacitor arrangement with the load. And at resonance, when you resonate this system, you have minimum input current. Okay. What you're actually creating here is called a phase conjugate mirror, or a PCM. And that's what Tom called it, a PCM. It's where you have these opposing wave actions acting magnetically, and then you have your capacitor and load configuration here. And that creates this phase conjugate mirror. And this is where time reverses, and you get this free energy effect of the scalar wave function. And this is the device that I built. I have several different transformers here, and this sets up your opposing configuration here with the capacitor. Then you put your resistive load. I got my patent back in December 31st, 2020. And of course, Tom lectured on this subject back in the 1990s. PCM resonators. Outputs a time reverse transverse EM wave. The output becomes more efficient. Efficiencies can easily exceed 100%. It's no problem. The device outputs an anti-gravitational wave as well. Decreases its own mass acceleration effect. The wave can become negative or less than zero. And of course, John Hutchison demonstrated that when he mixed his Tesla coils. The output of his 2 Tesla coils, he was able to levitate that 90-pound, what was that, a cannonball? I believe that was a cannonball. 90 pounds, he floated that. Examples of PCM resonators. My split flux transformer. Now, if you look at the original patent on Nikola Tesla, he of course had 2 coil, a dual coil arrangement, and you can operate this in an opposing field configuration. Then of course, Stanley Myers in his water car, it's right there in his patent. You can see that in his patent, the opposing coil configuration, and then he would tune the output of this opposing coil configuration with a couple of extra coils that are tunable, and you can tune out and match the opposing waveform configuration. And that, of course, will boost your efficiency. Floyd Sweet had a similar device with his VTA. Tom Beard's MEG device, it's very interesting because when you study his patent, you would see that it's just an ordinary transformer arrangement. And to me, my opinion here was that he hid that. His dual opposing coil configuration, he did not show that in his patent. But to get the scalar wave function, you would set up the MEG device in this opposing field configuration and tune it with these 2 side coils he had in his patent to get the scalar wave function. And then, of course, metamaterial resonators. And that's what Jack Sarfati speaks about in his lectures. I believe this the scalar wave functions actually occurring inside the material, that you excite the material with an electric field, that would be your sine functions, creating within the material your sine squared scalar function that is anti-gravitic and time reversed as well. Okay, next slide. This is my patent showing the converging magnetic material here and how you would excite that using a sine wave. And that's my patent number. I filed it back in 2015. Next slide. PCM resonators. This is what Tom was showing in some of his lectures there, what a PCM is. And that would be your wave functions, wave 1 and wave 2, your two sinusoid functions, setting up that convergence, okay? And so that would create your sine squared function, and that sine squared function would be time reversed. So that's your anti-gravitic time reversed wave. And that EM wave would add to a sine wave input. And I'll show you what that looks like. Okay, so your output of the PCM, output of these transformers, you'll actually see a wave that, well, I'll show you the trace in the next few slides here. But this is your scalar waveform, and it's shown as time reversed. Okay, that's your sine squared term. So the next slide, electric force versus the gravitational force. And you'll notice that the electric force is insanely huge compared to your gravitational force. I mean, 10 with 42 zeros after it. That's your electric force here compared with gravity. So gravity is not zero, all right? It's not zero, but it's damn near zero. Okay, next slide. Now, is there a link between EM and gravity and anti-gravity? And so that's really what we're doing here, is creating this time reverse scalar wave function, which is anti-gravitic, okay? And so with your gravitational equations here, you would have the longitudinal component, but your time will be time forward. Your anti-gravitic field is time reversed. And I was able to do an experiment. I replicated Boyd Bushman's experiment where he dropped magnets. And believe it or not, magnets bend space-time. They not only create a magnetic field, but magnets also bend space-time as well. And I was able to do an experiment that Boyd Bushman, I replicated his experiment, found out that, yeah, this guy's right. This Boyd Bushman is right. He was a Lockheed weapons developer, Lockheed Skunk Works. There's a fellow here that interviewed him. There's a video you can find out there on the internet about Boyd Bushman and his gravity drop experiments here. I extended Boyd Bushman's experiment using just magnets. And I found out that magnets fall faster than, let's say, your test rock. But when they're set up in this posing configuration, your magnets are opposing, it becomes anti-gravitic and they fall slower than the test rock. And I thought that was really fascinating because, and I'll get to that next few slides here. This was a video that I found on the internet here. For some reason, they took it off. I don't know why, but they took it off. You could probably find it on the Wayback Machine. But this shows the double photon configuration here, where you can take the frequency of that photon, that sine wave, and square it. And that comes out of this quantum field theory. And when I saw this, I said, hey, wait a minute. That's your scalar wave function right there. That's your sine squared term. So the scalar wave shows up in quantum field theory. And so that's where your mass comes from. And of course, Tom said matter is made of all trapped electromagnetic energy. So I thought that was interesting. Next equation. Okay, next slide here. This is my test bench. And what I'm showing here is my transformer. You'll see that on the right, and then a load capacitor. And that's generating a scalar wave function. And you see here on this next slide, okay, there's your input waveform, sine wave. The second graph you see here is the scalar waveform, and that's where you square the frequency of your input sinusoid. You get a scalar function, and that gets added to the sine wave. So you get a waveform that looks like this. Okay, this is where the two waveforms are added together. And lo and behold, that shows up in my test. The blue trace is your sine wave plus the scalar wave term, and below is your sine wave input. So there's your scalar term here. And that wave, just by matching the coils, see, the key to this thing is matching your coils. And the closer you get that zero function to what Heaviside would call zero, the greater your scalar wave function is. Okay, so the greater that wave function that you see, let's go back here. So the scalar waveform can be huge, can be absolutely gigantic. And of course, that would be your anti-gravitational term as well. Okay. And so, and I think, who was that? Floyd Sweet said something like 1,000,000 to 1, 10 million to 1. And of course, his device exhibited anti-gravitational effects. It became lighter, according to Tom. Okay, so the lifters. Dan Davidson came along here a few years ago in Tesla Tech and gave a lecture on what's called the Wilson-Lear anti-gravity lifter. And of course, he had these counter-rotating magnets that he was rotating on a plate. And I thought that was very similar to what Alexei was doing in Russia here with the Graviflyer. So people experimenting with the Graviflyer, I would suggest that opposing fields would be the key to this thing to get it to lift off the ground. And so the next slide here, the Alcubierre warp drive, I was fascinated with. And here I know that magnets bend space-time. So what does that mean? Well, geez, you can create a warp drive out of this, where magnets in the attractive configuration would bend space-time in this negative direction here. And then the anti-gravitic side would bend it in the positive direction here. And that would create your warp drive function. And so isn't that what Star Trek is using? Because Star Trek, if you only knew the original story behind Star Trek, is that the authors, and I wrote about it on Facebook and LinkedIn, and it turned out that my wife, Royal Light here, was married to a channel, and the channel knew this guy by the name of Jacques Dubier. He was a fighter pilot back in World War II, and he would have these encounters with these ET craft while in flight. And he became a channel himself and channeled this information from these ETs. And so he would have sessions. He moved to LA. He would have these sessions, and his organization was called Mind, M-I-N-D, Mind. And believe it or not, the authors who wrote Star Trek, the original Star Trek series, would come and visit him in his sessions and ask him questions. And he would channel this information from the ETs to these authors. And that's where they got all these stories from in Star Trek and their technology and like the warp drive. And this is pretty much how you would do it, this kind of tech. So the next slide, I'm not anti-gravity, but our technology is. That's my business card. And what I want to do is start a space program with anti-gravity using the scalar electromagnetism, only because the zero vector is not zero. And that's the show. That's my presentation. And here are some references you can check out. I recommend this movie. If you get a chance to watch a fascinating movie called Tenet, T-E-N-E-T. I would highly recommend watching this movie because you'll see anti-gravity in action, okay? You just run your film in reverse where things just fall up rather than falling down. That's anti-gravity. That's time reversal. And then, of course, Tom Bearden's psychotronic lecture. You can see that. Tom was interviewed here on evolving ideas. There's a psychotronics lecture. Scalar physics. My interview with Steve Ellswick. I also had an interview the other day. I'll post this on my Facebook and LinkedIn. And that's my presentation. And that's the show.
Thank you, Bill. Thank you, thank you, thank you.
Something to think about.
Yep. So I'll stop sharing there. Okay. And so anybody have questions on Bill's stuff?
It's a lot to take in. I see everybody's still mesmerized.
Okay, what does it do?
So,
okay, you build the thing with the coils and you hit the
Right.
button and you charge it up, and what does it do? Does it float?
It's a transformer. It's a transformer that cancels the magnetomotive force in your magnetic material. It sets up that opposing field action, but it has this output. You can still run things on the output of that transformer.
Can we try something? Let me try asking a different way. What can I take a fluke meter and hook this thing to it and see it making free energy? Can I make a thing float off the table?
Well, it depends upon how well matched your electromagnetic waves are. If they're matched perfectly, the scalar component is going to be gigantic. Now, I ran my measurements on this. I was getting like well over 90% efficiency on my transformer. And to me, I thought that was highly unusual. And so I was seeing that scalar function that was added to the sine wave. And that's what you'll see on your oscilloscope, is the scalar wave function added to your sine wave. Yeah. Believe it or not.
What does that mean?
And that's what they're doing. It means that there's time reversal going on in your device. Time is running backwards.
Great. Can I measure this with a thermometer? Can I measure this with a fluke meter? Can I measure this with a clock?
You can replicate Boyd Bushman's experiment where he takes two magnets and forces them together, two neodymium magnets. I just epoxy them together. And then you take that, kind of wrap it up, make it look like a rock. And then you have a rock, your test rock. And then you go to a high place, some high place. and drop them. Now, he used the elevator shaft at Lockheed to do his experiment with. And every time the opposing magnetic fields would fall slower than his test rock or whatever he was using.
So Bill, when the magnets hit the floor, do you like go back in time? By how much?
Well, the field is local. It's right there with the magnets.
You got to be stuffed in between the magnets in order to experience the time reversal, right?
Yeah.
I did hear that.
Right, stuck between the material of the magnets, just like the
Okay,
physical
guys,
material the
I don't mean
magnets
to
are
see you
made of,
dance.
and right outside the field poles.
Guys,
It's a field effect.
You drop a rock and a hammer. If they're both aerodynamically identical or you're in a
Yeah,
vacuum.
that's what the astronauts did.
I know what
A feather
exactly what they did.
and a hammer.
I know. So if everything is perfect and you put these magnets together,
right?
Does one fall a second faster than the other, or
Right.
a nanosecond faster?
Yeah, you can see it if you videotaped it. I used a height of about maybe 30 feet. You can see the effect where the opposing magnetic fields, the magnets, would fall slower than the test rock. So I replicated what Boyd Bushman spoke about. I said, boy, the guy's right.
Right. To answer
But
Drew's
then-
question, it's a couple inches over about 9 stories.
Yeah, I thought it was
It's
like
on that
seconds,
order.
right?
See, the fields are not perfectly balanced, okay, with these magnets. They're not perfectly balanced. But if they were, then of course it might even float. Okay, it's that anti-gravitic. But the fields really aren't that, identical at all.
So
But
how
you
does it
can
know
replicate this and try it out yourself.
I want to point out
There's a video. There's a
There's a-
video that Boyd Bushman spoke about. David Serrata did the video on this, and he published that video. You can replicate his experiment, and the guy's right. Now I extended it, okay, using magnets in the attractive configuration. Kind of wrap that up and found out that the magnets fell faster than the rock.
So Bill, I think what I would say would be that one of the things that we have here in terms of like all these different potential phenomena or effects that maybe can be measured, I think if there's a common, theory, like for example, here I'm dealing with the Mach principle, here at Woodward's lab, we're doing the Mach effect, which is something that he derived from that. So one of the things that I'm saying, trying to get to the point as quick as I can. But one of the things that we were challenged was, hey, we have one configuration of the experiment. Can't we think of other configurations that prove the same fundamental principle that we're trying to show? And I think that's one of the things that, okay, you might have one experiment and that could be, something that people could replicate or might be difficult to replicate. But if you have a bunch of different types of experiments that all show that, okay, there's something there, as we see with what's happening with, cold fusion, cold fusion was something that a year ago, I thought it was debunked 25 years ago. And I come to find that, no, it's been worked on. And now there's a bunch of replications and there's different experiments with different types of ways of finding that, basically microscopic fusion, however it's happening. And so there are some key, a few key things that need to be in there for something to be replicated. I think that's one of the, this is something that I've been talking to Jim about, is in terms of the theory, like there's experiment and then there's theory. And I think that without a solid foundation or a solid kind of at least an inkling of what the theory is or what's happening. And it may, you know, it may turn out that we find out later that, okay, we were wrong or whatever, but just have an idea of what that is and what could be the point of view that gives us, you know, that common understanding. So having multiple experiments and clear explanation of, okay, here's the principle at work, and this is how it's at work in this experiment, you know, experiment A, B, C, D, different configurations. So it's an effect that you can do these different things, and here's you know, here's what shows it. And so what you're describing sounds a lot like, you know, you know, the common themes that we're talking about. I think this it's something that you know, these particular experiments may or may not show it, right? Because there could be other things going on. It could be when you drop there, there's metal, there's other effects. And this is something I often say to Jim, is that we need to take into account these common kind of mundane physical effects. And you know, not everybody's going to be convinced. Even if you argue it away, you could have null tests, right? So you can have null tests where, you know, you do put magnets in the chamber, and you see if like the magnetism is like affecting it. Like, you know, you could do variations of the test to kind of reduce the likelihood that those things are happening. But when you have subtle effects, it's tricky. It's like to be convinced that there's something there, it takes a multitude of experiments and a well thought out experiment. And one thing I'd suggest looking at is like, for example, like we all know about the big rock that fell to Earth that killed the dinosaurs, right? That whole theory was so contentious. You know, they had evidence, but the mainstream was at the time was just like fighting it tooth and nail until that big crater was found in the Yucatan, right? And then it was like, okay, it was kind of like staring us in the face. But you know, that's the kind of thing that we're dealing with here, is that these are subtle things, and all the experiments we're working on can have mundane physics explanations. So we need to be very, you know, savvy about how we go about you know, making the argument generally. Anyway, I just wanted to say that, put that out there for you guys to consider.
But yeah, I agree that magnet dilates actually dilates time, because like I was showing the other day with the interferometer, moving a magnet next to a laser on an interferometer, you could see the laser being deflected. So there's time dilation, acceleration. They both are linked together. So I agree that magnets are changing the time.
Yeah, and one thing to keep in mind, time is, when we measure time, we're measuring electromagnetic phenomena. Okay, I mean, just let's be honest with it. The only thing
Time is a field.
measure when it's like not electromagnetic is okay, if we're in a gravity well, we're sending electromagnetic energy, we can see a redshift or time dilation. So if you have GPS, you move around. GPS or actually just even an atomic clock, you move it around, you're going to see time dilation happen. So there is a gravitational relation with time as well. So it's kind of a tricky thing. You know, when we're saying that time slows down, it could be that what you're affecting, because remember, time, if you talk about the speed of light, what you're actually talking about is the wave speed of the electromagnetic radiation or the gravitational radiation, right? So that wave speed, so something's waving, and there's a wave speed that can be identified. And that's the speed of light in a media. So when you change that, you're changing that wave speed. You call that time. You're not necessarily changing time, you're changing the wave speed, the speed of light in that media. So there's a distinction there that we got to be careful of.
Awesome. Okay, if it's okay, let me go to Zoltan, who has his hand up. Zoltan, go for it, sir. And can I ask you to turn your camera on?
Sure. Is it up? Sorry, it's kind of, yeah. Is it up?
There we
So,
go. Okay.
What I would like to ask is, can we go into this zero, minus zero is not zero? Because I believe that's where the physics has disappeared when we went from Maxwell to Heaviside. So can we, or is it beyond the scope of our talk here, or can we go into that aspect of the talk, please?
Okay, well, Heaviside came along and simplified Maxwell's equations. Maxwell's equations were originally written in this quaternion form.
I realize that, but I mean, can we actually go into the details, like what exactly Heaviside's role?
Well, Heaviside, all that he did is that you just set the zero vector because you have these opposing field. You have this opposing field action. You just set that equal to zero. All right. And so what the original Maxwell equations were is that it's not zero.
But we do agree, right? That is the place where most of the physics disappeared, actually.
Right. Oh yeah, with Heaviside. Heaviside simplified the original Maxwell equations. And that's what's taught in all the universities teach the Heaviside Maxwell equations.
Right. If I may, so epsilon and mu both were considered variables in the original quaternions.
Exactly.
That's what equations, they were gauged out as being considered always starting at a value of zero. They were variables in amplitude starting from a gauge value of zero, always at your pre-existing conditions. So just consider that if you have a magnetic field already present and you try to put another magnetic field into the same space where there's already a field present, it won't necessarily polarize that space in the exact same amplitude that it would if that field started out as being exactly equivalent to everywhere else around it, or if it didn't exist. So the point is that if you have an electric polarization or a magnetic polarization at the beginning of when you inject an electromagnetic wave, the wave doesn't behave the same. And that happens through epsilon and mu.
Yeah, you get the scalar function. See, the waves go like this and bend. The energy has to go somewhere. It can't go to zero. The energy has to go somewhere. And so it bends into this other direction, and you get this anti-gravitational effect from it.
Yeah, like balance is not permissible.
Well, there is no
zero. I mean, if you really wanted to stretch the boundaries, you could go into phase coherence of the physical structure of vacuum itself. And for that, you need a theory or a theoretical model which supposes that the aether is actually made of some physical material that can be polarized or turn and has a magnetic moment. And so one of those models is the positron-electron model, where you have positronium nodes and there's an entire assemblage along some kind of three-dimensional lattice structure. And these nodes, they can rotate and they can also expand or contract depending on the diameter of the rotation. So you can study positronium matter-antimatter interactions to understand that model a little bit better, and it's been proposed by many. But that's one way that we can actually explain these effects and this phenomena, and it seems to apply pretty well in laboratory experiments, which is why I would support that type of structure.
Mm-hmm.
And also in the Maxwell formulations, the gravitational shielding effect. And you say it anti-gravity. I prefer call it gravitational shielding effects. Were built into it. So with the Maxwell formulation, probably you don't even need quantum field formulation to come up with the gravitational shielding effects.
Is there gravitational shielding? Or, shielding
I don't
effect?
like this.
Is
Actually,
it
I
for
don't
real?
like this word anti-gravity. I call it gravitational shielding or gravitational.
Mm-hmm.
I just don't like this term anti-gravity.
I think that's a question in terms of Okay, so there has to be some kind of mechanism that we understand for inertia, okay? And what a matter field is, and the inertia it has versus the force fields, electromagnetic fields, and the gravity fields. So without that understanding or without a mechanism of that interaction, I mean, it's hard to say. So the theory that I covered, the Mendel-Sachs theory that I covered in several presentations, I don't know if you've seen it or not, but there's a mechanism in that theory for where inertial mass comes from. And that in that theory, the inertial mass would come from the interaction of a matter field with the local background pairs, as Sachs used to call them, and which was mentioned here as kind of like a ground state positronium. You could think of it that way. And that's where the inertial mass, that coupling is where the inertial mass comes from. So if you're affecting those background pairs, then you can affect that inertial mass of that electron field. So any given theory has to have a mechanism for this, you know, in terms of like, that's what I was mentioning before, is like have a theory that like describes, okay, how do you get there from here? So we can just see like, okay, here's a phenomena, we can do it. Okay, maybe we can do it, but we might not understand it, so we can't perfect it. So if we have a theory, we can test it, understand what we're doing, and then maybe do it even better or know what we're doing. And you know, that could lead to other discoveries and other useful applications of being able to do that kind of shielding. But is that kind of shielding something that we can demonstrate readily? You know, that if we were able to do that, you know, then we could, you know, levitate stuff, right? So that's the trick. Can we levitate something, and do we have a theory that describes, you know, with known physics, you know, or at least allowing for known physics, describes how that would happen?
Man, Sachs theory may be one of the closest I've seen so far that you presented. I wasn't even aware of it before you, Curtis, presented it on another open mic session, and absolutely amazing concept. It's the only one that I have right now that I can say like genuinely matches my vision and where the theory that I'm presenting came from and how I was able to match it up with other theories that already exist. I just want to jump over to HFK, who has been like the only one patiently, properly following the rules and raising his hand. So let's jump over to him if we can.
Okay. I have a couple of questions about the transformer you built. How are you driving it? Are you driving it from a AC powered, a wall powered transformer, or are you running it from a battery to isolate it from AC inputs?
No, this is basically the configuration here.
Okay.
So the input is being driven by an AC source, and the output is AC, but it has that scalar component in there because of this opposing configuration here.
Okay.
Yeah, I think he's asking if you can run it off battery or a generator, though.
A battery, any power, AC power source.
No, why
It's
I'm
the-
asking
it's the
is
same
that
thing.
why I'm asking is all of the stuff that I've read put out by Bearden suggests that isolating the input and also the output from each other, you get the anomalous effects more pronounced. I think the way he put it was not killing the dipole was one of the things that he kept on saying constantly. So when this is running, do you also see any anomalous temperature effects? Do you see cool downs on the transformer coils?
Well, I see an increase in efficiency,
which
is what I'm expecting here. And that's pretty much the extent of my measurements.
Okay. The scalar component that you see on the scope,
Hmm.
are you able to have a detector, a Faraday cage shielded detector that can pick up that component that's coming out of the transformer?
No, I haven't went that far with it. I just see the two waveforms added together on the scope. The scalar plus the sine wave and the sine squared term are added together on the output.
Have you tried filtering out the sine wave component and just having the scalar remain?
Well, just modeling it, I use MathCAD to model it. So I try to get something close to it to see what the waveforms look like. But that's pretty much the extent of it.
Okay, because what I'm asking is if you're able to generate the scalar component, can you then isolate that scalar component and see what effects it has in and of itself?
Yeah, I think you can. But see, you do that with opposing magnets when you force them together. They have very interesting effects, especially with healing. Healing is a time reverse process. The healing process, it's time reversed.
Yeah.
So
Well,
this technology would accelerate that
because some of what this, with the John Bedini circuits and the anomalous effects that he's reported over the years, with when the devices are working, you're getting anomalous cooling effects.
Right.
In particular, driving a system with a battery and then isolating the output to another battery and seeing that second battery, the receiver of the energy that's coming out of the circuits, getting cold. What I'm asking is, have you been seeing any of those anomalous effects with what you're doing?
I haven't gone that far with it.
Okay. So no scalar detectors that are detecting just.
See, what I'm looking at is circuit efficiency was my focus.
All right.
I'd like to point something out about your device, William. That the fields are opposing in their being fed AC during the top half of the AC signal. They will be opposing each other, but in the bottom half of the signal, they will be attracting each other, and then again opposing. Just I thought I'd point that out. If you want to give it DC pulses, they will always be opposing. But if you're feeding them AC, it'll be opposing, attracting, opposing, attracting. The signal goes up and down.
Yeah, see,
well, I mean, technically in his first diagram, Michael, it doesn't, they aren't going to be opposing and attracting because they're both the same number of turns on opposite sides of the core. And so both of them will create opposing fields on one half of the cycle, and then they will create more opposing fields on the other half of the cycle because both coils are effectively fighting each other in either case. They're not being switched on and off. So in his basic diagram there, you're always opposing during both halves, but you do have to create the moving electromagnetic field. So that means you have to create a change in the current flowing through the core over time. It obviously doesn't work if you just pass DC. So.
You see, a really interesting thing they do is that they put magnets in their device. Floyd Sweet did it. Tom Bearden put magnets in there. And I think that the reason why they use magnets is to shift that scalar wave function, is to put a shift in that and to make it look more like AC.
They use magnets to partially saturate the core ahead of time. If you look at the BH curve of a core material like Met Glass, for example, in Tom Bearden's MEG, or the variety of other materials that have been used that are very, very high speed, including black sand for the Miller device. Or the Molar device, sorry. What you'll see is extremely fast reflux times, but prepolarization from an external magnetic field. Even in pulse motors, where the external magnetic field is on a rotor that's flying past the core, you end up with this partial saturation, right? So if you're going to put an impulse into this coil, then it'll reach complete saturation. What that means is you get an alignment of all the dipole moments for every single domain inside of your magnetic material, as much as is achievably possible in the engineering. So what happens when all the dipoles are aligned when you get these domains? Well, you get this possibility of a new kind of wave traveling through that core. You get a polariton, which is this flip, and you can also get what's also known as a spin wave. So for that, I'd recommend Greg Hughes' stuff, Vasant Corporation. Take a look at spin waves and the variety of NMR-related materials there. This spin wave, anyways, it's interesting because it's a coherent wave. So that means the whole core is at a point acting like a coherent lattice structure. It's able to create these coherent states, which means if you affect one part of the core, you're affecting kind of the whole thing. And because it has some physical three-dimensionality, it takes up a certain amount of volume. That means that vacuum space that it would otherwise be taking up in the areas between the atoms is no longer available because it's been polarized along the same lattice structure. So you're looking at that possibility there. Even, what's his name? Stan Dale talks extensively about this as well. And I'm sure you know his work.
And on the transformer, this is a continually powered, or are you doing any pulse power?
I'm just using a sine wave generator.
So continual sine wave, no interruptions.
No.
Okay. All right. Thank you.
Yeah, the whole idea was to replicate what Tom was doing, but also getting that sine squared term that I wanted to see. And then that ties back into the original Maxwell equations that you see that sine squared function popping up. Then also in quantum field theory, you have that sine squared function as well.
Okay.
Awesome. Okay. Well, so we've got guys, we have about 20 minutes left. I think we'll probably close things down at just about 8. So did anybody else have questions for Bill, or does anybody else have anything to share in the next 20 minutes or so until we close up shop? Crickets, crickets, crickets.
Honestly, about the new image that you put for the new APEC. Where did you get that image for the upcoming APEC?
I got that from Adobe Behance. I'm working with 4 or 5 artists, and those are AI generated images. So,
because I saw something in the sky that looked like that, maybe about a week and a half ago, and it was a one frame look, and I happened to be turning like this, and I saw it. When I looked again, it was gone. So it sparked, a light bulb in my head when I saw that, image of the new, and I was just, where'd you get that? It was just, I don't know.
No, I appreciate your asking.
Yeah.
So yeah, with the original APEC images, I bought stock art. I own a lot of stock art, the whole 9 yards. And so for the first couple of years, we were doing that. And it reached a point, part of it is like the new AI images are a lot more photorealistic than the old ones are. And then the other part too was it's just like, okay, here's a picture of a planet, here's a picture of a UFO, it just get kind of repetitive. So, so what I started doing was working with 3 or 4 different artists who do space images. And I started it because I love their work. It's incredibly realistic. Over time, I learned that mostly what they're doing is Midjourney. That's primarily what they use. So there are a lot of tools out there, but they're primarily doing Midjourney. And then I think that there are a couple of tweaks and like an upgrade you have to do for the high def or something.
So it's an AI. It's not. Okay.
No, those are all AI. In fact, I was kind of surprised that they're getting pretty good. Let me show you.
Is it better than OpenAI DALL-E?
I am not sure.
Midjourney is fantastic. Nobody's played with Midjourney. My God.
Yeah, so this one is not from one of our artists. I actually purchased this one online, and I purchased this because I love the image. I used this for an APEC conference, and basically when Mark gave me specs for the website, I tried like 30 different images, and this was the one that everybody kind of liked the best. This image here is actually AI generated also. I'm not sure what I'm not sure what platform it was used. I actually asked the person who created it. I said, can you create different versions and variations? Because I want to use them in different places on the site. And he said he wasn't willing to. So, you know, this thing is at least a year old, right? So the level of this is moving forward rapidly. Now, in this case, I could be mistaken, but I believe this was done in the style of a Japanese painter. And that's one of the other things that you can get with a lot of these AI is if you tell it to recreate an artistic style, usually it has enough loaded that it can at least come close. And in this case, I saw something about 6 months after I bought this one, had nothing to do with UFOs. It was just like lakes and stuff like that. And then when I looked it up, I was like, oh, I get it. Okay, it's emulating their style, but it's doing it through AI. So yeah, I mean, you know, it's moving forward really rapidly. And Adobe Behance, if you're feeling bored, Adobe Behance is an interesting place. Let me see if I can find the Russian space shuttle for you. And that's that. And here it is. Here, I will, let me share this one. Oh, might take me a sec.
Talking about the Baran from the 80s?
Yeah, but it was.
Yeah, that was a US space shuttle without all the EOs that fixed all the mistakes. And some jet engines on the back for some unknown reason.
Now I'm having trouble. Oh, here it is.
Ashrish, you're on live screen now.
What?
You're on live screen.
What?
You're on the big screen.
Oh yeah. Yep.
Okay. Yeah, I'm having. Oh, here it is. Here we go. Here we go. Here, and I'll drop this one in here too. So there's actually a fair amount in there. Let me share this one for you guys. This is not advanced propulsion, not like we think about it, but it's still interesting. This was a couple of Russian guys, a couple of filmmakers, and you could see if you go in there, and I'll drop this link into chat in just a moment. These guys basically went to the old abandoned hangar for that Russian shuttle, and they shot a bunch of photos of it. Pretty cool. Now, I could be mistaken, but I think I've heard that since this was done, that hangar actually collapsed.
It did.
Okay,
And
so
those things are buried under the ceiling and a lot of ice and snow and garbage.
yeah, and there's the filmmaker. And when I get down to the bottom, they actually shot video of the entire trip too. So they have, yeah, so this was all shot in the hangar. This is the old Russian program. There it is. So it's not surprising that it's collapsed. I mean, this thing is kind of very decrepit there. And if I remember right, this was out in Kazakhstan. So it's like just way out in the middle of nowhere, right? They were trying to put it far south, if I remember correctly. Yeah, and there's their trip journey too. So yeah, let me here. I'll put this one into chat.
The actual Energia, the rocket that the shuttle rode up on, their shuttle, was brilliant. That Energia design was absolutely brilliant. From a rocketry standpoint, the shuttle was a joke, but you know, it did orbit the Earth once and fully autonomously landed.
Well, you know, I interviewed Paul Siz, and he was an old timer. He was one of the hypersonics pioneers. He pretty much invented Aurora and you know, that dark star or whatever they're calling it these days. He built the engines for it that came out of the NASP project. And one of the things that he had said was, so the original program was Air Force, and it got handed over to NASA. And NASA basically the Air Force had a plan for reusable rockets back in like the 60s that were just like Elon Musk's. I mean, they weren't as advanced, but it was that kind of idea. And they were like, look, here's how we could do this the most cost effectively, and we could start a real program. And NASA, they had a healthy dose of not invented here. And so NASA basically just said, look, we don't want it. We're going to do it our way. And they did the shuttle program. He felt like that set the entire thing back like 40 years. So
there was zero love between the Air Force and NASA.
Yeah.
And the Joint Air Force NASA nightmare programs, because I touched those when I was a young engineer, they were horrible. NASA was hated by the Air Force for good reason, but that was a shotgun wedding made in hell.
Yeah. So I don't know. It's interesting, you know, and then it's interesting to see what SpaceX is doing for it, right? I mean, you know, they're revolutionizing the space industry. I don't know if you guys have looked at any of those satellite maps, how many are up there right now, but I mean, the Earth or the sky is littered with satellites. There are thousands.
I used
Well,
to 15, 20
that's
years ago, I used to go outside and look at because I got a pretty dark sky here I'm just north of the Space Center, about 30 miles. And it's very dark sky. And I used to be able to go out there and do my astrophotography. And I would see maybe 2 or 3 or 4 satellite crossings an evening with binoculars, many more. Now you go out there and there's 150 of them before it gets really dark enough for the curve of the Earth to screw it up. It's terrible. It's just depressing. I don't see how anybody does astrophotography anymore. The frames
that's
would
what
be
I was
littered.
getting at. Yeah. Yeah. It's getting cluttered too much. You know?
No, I've got a kind of general question here, and I don't know if anyone here has heard of Stoyan-Sarge or the concept of heterodyne resonance, which is an ion-electron coupling. But so let me just first ask: has anybody heard of that at all?
I'm familiar with Stoyan. I think I'm connected with them on Facebook.
Okay, well, I'll explain heterodyne resonance in real quick.
I've heard
here.
about heterodyning,
So-
but I feel like some guy. Let's see. Dan Winter was talking about heterodyning in one sense, but he worked with this mathematician where it didn't really make sense of it. So maybe there's some better way to look at it.
Here's kind of what he was doing. So he found that if he had electrodes in certain gases ranging from atmospheric pressure down to partial vacuum, and he would generally use nitrogen, argon, helium for his experiments. What he found is that off the electrodes, you would end up getting free electrons generated, and they would fly off the cathode, but they would bombard and create electron cascade. And what would end up happening is you would have ions that were positively charged trying to chase an electron. Or I guess you consider it kind of the other way around. The electron is lighter, so the electric field that accelerates the electron once it's stripped off of some atmospheric gas particle starts to produce cyclotron motion as a result of trying to catch up to the center position of where the nuclei is, the opposite charge protons, right? So in its production of cyclotron motion and its rotation around, it decouples somehow gravitationally. And if you get a lot of these things running in parallel lines, a lot of these electrons producing cyclotron rotation and ions following them that are lacking that one electron trying to neutralize, you can oscillate them back and forth. And it seems to have some kind of gravitational shielding effect or surface shielding effect that not only affects the gravitational attraction, but seems to reduce, almost eliminate the inertia of anything that's enclosed inside the plasma envelope. Where have we heard that before? So we look at those Navy patents, right? And we've got the same plasma envelope stuff there. So it's one more thing that I don't think a lot of people are looking at in consideration of the Gravity Flyer or the KDM physics Levity device, or a lot of these other types of technologies, even including T.T. Brown. No one's really considering the idea that you can generate resonance modes between oppositely charged particles or by ionization, and how it might affect the refractive index of that local space.
Is the behavior following something like what happens in a Farnsworth fusor, where you have stuff zipping around the positively charged nuclei in the center of a fusor?
Really good analogy, actually. Yeah, you're getting some very similar behaviors there. It's just that they're sort of omnidirectionally disposed, and during the heterodyne resonance modes that Story and Sarge talks about, they're all along the same linear vector, so that means they're moving together in this sort of coherent field.
Is this thing circular motion or a spring-like longitudinal motion?
So in the center, your heavier ion, your nuclei that's lacking that one electron that got stripped off of it, is sort of wobbling back and forth. It's producing a very small type of rotation, but it's not moving, circularly polarized very much along the linear path that it's traversing. And the electron that's around the outside of it, well, that's taken a pretty large path because it doesn't weigh much, and it's being accelerated under the electric field potential produced by the electrodes. So the electron is being flung pretty far away from the nuclei, and the nuclei tries to catch up to it. They try to meet each other, but they never quite connect. So as long as the frequency is high enough, the electron stays separated from this positive ion, and the positive ion whips back and forth. The difference here is you end up with the electron taking more physical motion through space, but because technically it's exactly one electron off from the atom that it was stripped from, that electric field is different, so you have more negative potential as the geometrically amplified field. Go ahead.
Is this doing a donut, a toroidal shape? What does the thing look like?
It is doing a toroidal shape.
Okay, so this sounds a hell of a lot like Seward's electron spiral toruses, where Seward proposed and I think demonstrated fusion, where basically firing a pair of donuts at each other, and also proposed once the this electron spiral toroid was generated, you have the electron spiraling around the donut. You'd have the positively charged ions in the center of it, and this thing was supposed to be able to act as a storage device where you could load in idiotic amounts of megawatt hours of energy in a plasma donut.
Yes, exactly. It's a 3-order torr if you consider all the active systems.
And
just in the initial diagrams, he proposes a 2-order torr.
And one of the practical upshots of the donut is that you have literally megawatt hours of energy storage in there. And one of the applications besides nuclear fusion was, instead of having those nasty hydrocarbons inside of a fighter jet, which is 90% of the mass of a jet, well, you put in the donuts and you pass air through the donuts, and you're extracting out, you're heating up the air that's ingested through kinetic energy transfer, and goes out the back end, and you've got thrust. So you've got a jet that you literally is rechargeable and can go hours and hours and hours on the stored charge in the donut.
Yeah, that's incredible, and you don't have to pay for the weight of the fuel or anything like that. You've effectively built it up. It sort of reminds me of like superconductor energy storage mechanisms that are designed for instantaneous power delivery. They can release hundreds of kilowatts in a matter of seconds with no problem whatsoever, just simply by changing their temperature. And so, yeah, if we build this field up, what do we need for UFO propulsion, advanced propulsion, exotic types of energy systems? Well, we need some way of generating instantaneous, very, very high amplitudes of energy delivery. And the plasma torus is one such mechanism that allows us the ability to do both things. One, store up a huge amount of energy with very little mass, and 2, release the energy almost instantaneously by a field collapse.
Actually, just the opposite. It's not storing energy with very little mass. It's storing energy with absolutely no mass except for the equipment to generate the donut and keep it stable. Oh, and the donuts, there are patents, Seward, SCWARD. The donuts are stable at atmospheric pressure.
Wow, really?
Yeah,
So,
I gotta read that.
I mean, what you described, Jeremiah, is very similar to what I talked about with the background pairs and how you could like lower the inertial mass inside of a volume. If you're lowering the the density of that pair, that field, call it a background pair field, whatever. my question is, okay, is this something we can replicate and demonstrate that yes, we can lower and do this like reliably in a lab? And the other thing I want to bring up is, you know, there's a lot of mention of patents. Now, I would say that, okay, first, more than likely you would want something fully enclosed, but that's not necessarily the case. You know, we don't know enough about how the background pairs behave and whether just getting some of them moving or lowering that density just in the region, how that happen. We do know we're moving through space, so I can imagine that once you lower, you know, you're getting a shielding effect that would like really quickly you know, continue. Like you don't have to move it for it to happen because you're already moving. But the other thing is this patent thing. If there are patents, I know that the U.S. government has a law that it's basically a Invention Secrecy Act or something of that effect that was passed in the 50s, that if there's something dangerous enough that they could deem it a secret. So if there's going to be a physics advance and, you know, if there's a hypothesis that there are black projects, people already know how to do this, it's secret. It's a really tough thing to do. Like how do you do this and do it in a rational way where, you know, of course, you know, when we do these activities, if you do try to patent them, it could be something that just is taken away and out of.
Okay. Well, guys, so it's 8 o'clock. So what I'm going to do is I want to thank everybody. So I'm not going to close things down, but what I am going to do is stop recording, and then I'm going to find somebody to be a host. So let me do that. So let me thank everybody. This has been APEC Open Mic for Saturday, April 27th. And so I'm going to stop recording now.